Good morning, everyone. It is my great pleasure to welcome you to the 4th International Conference on Molecular Biology and Biotechnology 2021. This conference is held in conjunction with the 27th Scientific Meeting of the Malaysian Society for Molecular Biology and Biotechnology. It is my great pleasure to welcome you for this conference to be held last year at Molecular Biology and Biotechnology had to be cancelled due to the COVID-19 pandemic. This conference is held almost overnight. Most of us had to adapt to working from home and completing most of our tasks using some sort of an online. We actually planned for this. There was so much uncertainty at Molecular Biology and had to be cancelled due to the COVID-19. This conference is held almost overnight. Most of us had to adapt to working for the first time ever and completing most of our tasks and by using some sort of online. We actually planned by doing there was so much uncertainty and travel complexities and by had to be cancelled due to the COVID-19. This conference is held almost overnight. Most of us had to adapt to working for the first time ever and even while and by using some sort of online. We actually we have there was so much uncertainty joining us from more than had to be cancelled due to the COVID-19. This conference is held almost overnight. Most of us had to adapt to working for the first time ever and even while and by using some sort of online. We actually we have there was so much uncertainty joining us from more than had to be cancelled due to the use this conference is almost overnight. Most of us had to adapt to working for the first time ever and even while and by using some sort of online. Today we have there was so much uncertainty joining us from more than had to be cancelled due to use this conference is almost overnight. Most of us had to adapt to working for the first time ever and even while it is going to be today we have already so much uncertainty joining us from more than had to be cancelled and future use this conference while almost overnight. Most of us I am happy to say that even while it is going to be today we have already so much uncertainty joining us from more than had to be cancelled and future use this conference.
Okay, ladies and gentlemen, I'm sorry about that. We will restart the video again.
Good morning, everyone. It is my great pleasure to welcome you to the 4th International Conference on Molecular Biology and Biotechnology 2021. This conference is held in conjunction with the 27th Scientific Meeting of the Malaysian Society for Molecular Biology and Biotechnology. We actually planned for this conference to be held last year at a physical venue, but it had to be cancelled due to the COVID-19 pandemic. Almost overnight, most of us had to adapt to working from home and completing most of our tasks using some sort of an online platform. There was so much uncertainty created by the pandemic that the committee decided that in order for us to proceed with this conference, we have to do things differently. So, for the first time ever, we are excited to be able to organize this conference virtually. By doing this, we have omitted travel complexities. We are able to cut costs, reduce our carbon footprints, and the best thing is that you are able to log in from the comforts of your own home, even while you are still in your pajamas. Today, we have around 400 participants joining us from more than 12 countries, including Hong Kong, Thailand, Saudi Arabia, Nepal, Sweden, Nigeria, Bangladesh, Philippines, Iraq, India, Japan, and Malaysia. This is a truly an international conference in spirit. The theme of today's conference is Beyond 2021, Building Sustainable Science. In a world where maintaining balance is becoming more challenging, pursuing sustainable science is important to support long-term ecological balance. It is pertinent that science is geared towards solving problems to ensure the development of effective interventions to meet the needs of present and future generations while protecting the environment. I am happy to say that our scientific committee has curated a program full of exciting sessions for your benefit. For the next 3 days, we will have plenary and invited speakers who are biotechnology and molecular biology experts to share their experiences and discoveries with the rest of us. Topics will range from agriculture and aquaculture, medical, environment, industrial and food, and microbial. We are also very fortunate to have 2 distinguished keynote speakers for this conference. Right after this, our first keynote speaker, Prof. Datuk Wira Dr. Raha Abdul Rahim from University Technical Malaysia Melaka will be speaking to us on building sustainable science. Tomorrow, our second keynote speaker, Prof. Dr. Georges Nonu from University Pierre et Marie Curie, Paris, France, will enlighten us on the triumphs and vicissitudes of biotechnologies on malaria control. Make sure you do not miss out on any of these sessions. Before I end, I would like to express my sincere appreciation to the organizing committee who have worked tirelessly for the past 13 months to make this conference a reality. We are happy to have the support of a great cadre of sponsors. Allow me to list our sponsors: Research Instruments Sdn Bhd, Impaco PLT, ESCO Micro Sdn Bhd, Analisa Resources Sdn Bhd, Nanogene Solutions Sdn Bhd, Straits Scientific Sdn Bhd, and NextGene Scientific Sdn Bhd. Thank you very much for your generous support. Finally, thank you to all of you for registering for this conference and making it a success. I hope you find the conference both enjoyable and informative. Until we meet again in person, take care and stay safe.
Thank you, Dr. Amira. I apologize for the earlier glitches. Ladies and gentlemen, this year's keynote speaker is no stranger to many of us here. She is Professor Datuk Wira Dr. Raha binti Abdul Ibrahim, the current Vice Chancellor of University Technical Malaysia, Melaka. Prof. Datuk Wira Dr. Raha graduated with a degree and an MSc in microbiology from Oklahoma State University in the USA. She joined University Putra Malaysia in June 1991 as a tutor at the Department of Biotechnology, and then went on to complete her PhD in molecular genetics at the University of Strathclyde, Glasgow. Her main research interest is in the development of lactic acid bacteria for delivery of useful protein, plasmid biology, vaccine delivery, cell factory system, and lactic acid bacteria. Her other research interest is in the identification of genetic markers and authentication of halal products of molecular methods. She has supervised and co-supervised more than 80 postgraduate students, published more than 150 papers in peer-reviewed journals, and filed several intellectual property rights. She is also consultant to several government agencies and biotech-related industry. Professor Dr. Wira Dr. Raha has held several administrative posts at both the university and national levels, such as she was the Director of Research Management Center, Deputy Dean of Research Biosafety, Chair of Genetically Modified Organism at UPM, and was also the director at the Institution of Higher Education Excellence Planning Division, Department of Higher Education, the Ministry of Higher Education, MOHI. As the director, she was in charge of the overall innovation ecosystem as stipulated in the Malaysian Higher Education Blueprint 2015 to 2025. Her division specifically managed MOHI's research and development programs and MOHI Fundamental Grant Scheme, FRGS. In addition, she also coordinated the Matching International Industrial Grant, MyPair 2019, RNE database, MyRA and MyGrants, and facilitated activities relating to promotion of R&D products from the Institution of Higher Learning Malaysia. She is a National Science Council member, Board of Member for the Malaysian Examination Council, Council member for the Engineering Technology Advisory, and Board Selection Committee for National Academic Award and others. Besides being a life member of this society, the Malaysian Society for Molecular Biology and Biotechnology, she is also the past president of the Malaysian Society for Microbiology and the Malaysian Society of Lactic Acid Bacteria. She is also affiliated to several professional societies such as Malaysian Society for Molecular Biology and Biotechnology and the Genetics Malaysian Society. At the international stage, she is a reviewer for many index journals and a member of the American Society for Microbiology, and was also the Secretary General to the Asian Federation of Societies for Lactic Acid Bacteria. Ladies and gentlemen, it is my pleasure to invite Professor Datuk Wira Dr. Raha Abdul Rahim to deliver her keynote address on this year's conference theme, Beyond 2021, Building Sustainable Science. Prof. Raha, you have 30 minutes to deliver your keynote address. A bell will be rang 5 minutes before time. And ladies and gentlemen, for your information, there will be no Q&A after the keynote address. Prof. Raha, the screen is all yours.
Thank you very much, Madam MC. It's my pleasure to be here this morning. Thank you to the organizing committee for inviting me to share. Okay, hold on. I need to. Hey, it's gone. Hello?
We can hear you.
Yeah, but I can't, sorry, I can't see you all. I'm coming in again, okay. All right, okay, I'll share my screen. Share screen. We've done this before, don't panic. Okay, can you see my screen?
Not yet. I just can see you.
That's dangerous. Okay, hold on. Let me see. What do? I did the same that I did last time. Okay, let's try this again. I've shared my screen. Okay, share screen, yeah?
Yeah. And then you got, oh yeah, okay.
And then I've shared screen. So now I'm going just to go to my slides and share my slides. Okay, can you see it?
No.
No. Let me just ask for help here.
All right, okay.
Okay, hold on.
Video itu.
Okay, I'll switch off the video for a while. Okay, remember. Share screen. Okay.
You need to on your share slide. Your screen you share it.
No, this is one.
No, right from here. Not from there.
Okay.
Select the one.
Right. So now I can.
Yeah, have you on your ni?
Yes.
Tak on lagi tau, itu on ni. Baru on.
Okay, is that okay?
Yes, I can see a slide now.
Oh, put your PowerPoint ni.
Okay, phew. All right, sorry about that.
No problem.
Okay, very good morning, everyone. First of all, I would like to thank the organizing committee for inviting me to today's very prestigious conference, international conference. I will be talking about Beyond 2031, Building Sustainable Science, which is actually the theme for this year's ICMSMBB's conference. Right. Okay. What is sustainability? Now, there's a definition which usually I would like I like to start my talk with looking at the definitions of things that we want to discuss on. So the definition, this is from Oxford Dictionary, the ability to be maintained at a certain rate or level, and that is, for example, the sustainability of economic growth and avoidance of the depletion of natural resources in order to maintain an ecological balance. For example, the pursuit of global environmental sustainability. So in a nutshell, sustainability is the capacity to endure in a relatively ongoing way across various domains of life. In the 21st century, it can refer to the capacity for Earth's biosphere and human civilization to coexist. There are three basic pillars of sustainability. When you talk about sustainability, usually you talk about the social, the stability, the sustainability of social life, the sustainability of economic, the sustainability of environment. And all these can intertwine. And for example, if you talk about social, environmental, there's environmental justice, natural resources stewardship. You talk about it locally and at a global scenario. And economic, social, economic sustainability, looking at the business ethics, the fair trade system, workers' rights. And when you talk about environment, economic sustainability, you usually talk about energy efficiency, subsidies, incentives for use of natural resources. Now, what are the common issues related to sustainability? So questions crop up as long ago as in the 1990s, where people talk about what shapes the long-term trends and transitions that provide the major directions for this century. What actually determines the adaptability, vulnerability, and resilience of human environment systems? Unfortunately, actually, we are facing it now as we are actually attending this conference. How can theory and models be formulated that better account for the variation in human environment interactions? What are the principal trade-offs between human well-being and the natural environment? Can specifically meaningful limits be defined that would provide effective warning for human environment systems? Now, this is where perhaps science can come in to be a warning system, to give us warning. How can society most effectively guide or manage human environment systems towards a sustainability transition? And how can the sustainability of alternative pathways of environment and development be evaluated? Okay. Sustainable development is commonly defined as development that meets the needs of the present without compromising the ability of future generations to meet their own needs. We always tell ourselves that we must save the planet for our future, must save the planet for our children. This concept of needs goes beyond actually simply material needs, but also includes the values, relationships, freedom to think, freedom to act and participate, all amounting to sustainable living morally and spiritually. Now, each country, however, must respond to its own conditions and priorities. As you know, there are many divisions within the countries in the world, while breaking away from the current practice of growing first and cleaning up later. So different countries would respond to the different sustainability measures according to its own conditions and priorities. The universal transformation to a sustainable development in the next decade depends on the simultaneous achievements of individual innovative pathways that manage to make that break. Now, from there, the Sustainable Development Goals were formulated. It is actually characterized by three signature elements. One, balancing the economic, environmental, and social dimensions of sustainable development. Second, leaving no one behind. And finally, ensuring the basic requirements for the well-being of future generations. I'm sure you all are very familiar with the 17 SDG that was built on the Millennium Development Goals, but with significant differences between them, and also the processes leading up to their adoption. And the SDGs expanded the focus by integrating a wider development policy agenda addressing many aspects of economic, social, and environmental sustainability. Now, in an organization, sustainability is important. Why? Because according to McKinsey's study in 2019, companies with high environmental, social, and governance ratings, or in short, the ESG ratings, will consistently outperform the market in both the medium and long term. So we are actually a company or an organization. It is worth our while to look into this. Now, while sustainability strategies might be an investment in the short term, they can lead to long-term benefits. Now, how science can help to create a sustainable world? Science is critical in tackling complex challenges for humanity, such as climate change, biodiversity loss, food security, pollution, and also poverty reduction, as it lays the foundation for new approaches and solutions. Now, how can science best fulfill this commitment to society? How can dynamic connections be created between knowledge and action? Now, these concerns have led to a new approach that is known as sustainability science. Nada Al-Nashif, who is UNESCO's Assistant Director General for Social and Human Sciences, in 2016 addressed the conference, and she mentioned that this is a critical role for sustainability science, as it promotes cross-disciplinary approaches to advance the understanding of human-environment interactions and systems, and how these interactions affect the challenge of sustainability. And what is sustainability science? It is described as an emerging field of research dealing with the interactions between natural and social systems and how those interactions affect the challenge of sustainability, meeting the needs of present and future generations while substantially reducing poverty and conserving the planet's life support system. Flavia Schegel is the Assistant Director General for the Natural Sciences in 2016. I quote, "Sustainability science is an issue of a normative nature. It is an approach which will allow to capitalize on research as a tool to solve problems. It will assist in tackling complex problems related to sustainability from disaster risk reduction to food, water, and energy security to societal decarbonized path by informing the design of integrated sectoral policies based on the best scientific knowledge available." And as our Madam MC mentioned just now, by doing an online conference like what we are doing today, we are actually reducing the carbon footprints. We are actually saving some budget because there's no traveling. So these are the positive things that perhaps we can garner from COVID, the onset of COVID worldwide. Resilience and adaptation are essential conditions in our quest for sustainability, and this must be informed by science and other knowledge. Sustainable science in combination with education plays a key role in sustainable development. So the 2030 agenda of the SDGs, where science and technology are powerful agents of change for better or worse, depending on how they are steered, and guided by the 2030 agenda, intensified science policy cooperation can harness breakthroughs in our understanding of human environment systems to enable the achievement of the Sustainable Development Goals. Now, the urgent need for transformations towards sustainable development demands that we strengthen the directionality of science on behalf of a mutually benefit impact for humanity and the planet. And I'm happy to see that there's going to be some very good scientific papers that will be presented in this 3-day conference that can be shared to everybody. Now, the role of science, sustainable development, the global socio-economic and geopolitical changes are creating enormous challenges for humanity. The newly industrialized countries, especially in Asia, experience rapid economic growth causing modern society environmental problems. And this adversely affects sustainability with the cutting down of forests, with there are many things that is happening around the globe, especially in the Asian countries. The ecological problems caused by human economic activity are worsening and taking on global dimensions. Environmental and social conditions continue to worsen in many, many developing countries. If we are to move towards sustainable development, now our friends from the industrialized countries will have to accept special responsibility, not only because of their past ecological debacles, but also because of their present technological know-how and financial resources. Sustainable production and consumption involve not merely technical progress, but also cultural patterns of collective social behavior and values. So the values embrace two different meanings: utility of ecosystem science for resolving environmental problems and the socio-economic benefits and services conferred by a healthy ecosystem. Now, the immersion of values and behavioral impacts are very, very important for transformation-related sustainability science. Now, some of the values, the 4 important perspective values that I'm sharing with you here, these are surfacing implicit values that revolves around critical reflection on normative assumptions in scientific practices, negotiating values, which is related to the values held by different actors in group decision processes, eliciting values that focuses on the ascription of values to particular objects or choices related to specific sustainability challenges, and transforming values that highlights the dynamic nature and transformational potential of values. The immersion of all these values and behavioral impacts will play a very, very important role in communicating the values of ecosystem science. And there should be some tenable transformation actions. Governments at every level should institutionalize science policy society alliances, focusing on co-designing, implementing, and monitoring context-specific pathways to sustainable development. Now, the actors or the participants from science, policy, the private sector, and civil societies must all radically rethink their partnerships and create experimental spaces for collaboration on transformation pathways. Now, governments should enable co-creation of citizen science and testing of transformational ideas. Universities should fully embrace the mission of advancing sustainable societies by promoting education for sustainable development that would include teaching and learning, research, and services. Now, building the capacities and skills of the next generation of researchers and change makers is one of the biggest leverage points towards sustainability at humanity's disposal. Now, just in a nutshell, what will universities of the future look like? Would it be student-centered, interconnected, and striving for a better world? Customized, on-demand education, whereby flexible learning experience will be available on demand 24/7, a mix of degrees and shorter qualifications, quality career advice to compete for jobs of the future, must be a place for collaboration and entrepreneurship, and higher education's moment of choice where there should be exponential changes in technology. Now, people, my dear participants, my dear colleagues, we are actually now in the future. If you look at how how they designed this, and looking at the questions and looking at, you know, what was envisioned not too long ago, maybe a couple of years back, and we look at what will the universities of the future look like, we are actually here now. You know, things are 24/7 online. There's a mix of degrees and shorter qualification, professional qualification, professional certifications. There's a, you know, a push for entrepreneurship. There should be, you know, so it's student centered, it's interconnected, striving for a better world. So it's probably this slide is old. You know, what will universities of the future look like? This is where we are now. And quoting Professor Dewar from La Trobe University, personally, I'm drawn to what's called the ecological university, a university that's deeply networked to the society around it, makes its knowledge resources freely available, and engages actively to bring about a better world. I believe it's inevitable. It's coming. I believe it's here. Shall I quote also from a colleague of mine from UM? She says that UM has been doing that, you know, making itself an ecological university, and it's networking the society around it. Even in UTEM now, we also have what is known as technology at university, advancing society and industry. So we are moving towards the future, but I feel that the future is already now. I'll share with you some. This is also for the for our international colleagues, that we have the government has actually come up with several sustainable related policies in Malaysia. Some of these are familiar to most of us, I'm sure. The biotechnology for wealth creation and social well-being, Dasar Teknologi Hijau Negara, National Green Technology Policy, Green Technology Master Plan, the National Policy on the Environment, National Policy on Climate Change, and the latest is MySTIE, which is the 10 on 10 initiative from the National Academy, from the Academy of Science Malaysia. And in Malaysia, we also look at some of the rankings, especially the sustainable related rankings, and these are some of the achievements by several Malaysian universities. I just put a few examples here. So for example, we are into the UI Green Metric, where I think UPM is ranked number 1 in Malaysia and not that far away, probably top 10 in the world. And then we've got the THE Impact Ranking, where UKM is ranked highly. USM is also ranked very highly in the THE Impact Rankings, which actually look at the SDGs. And then we've got UNIMAS and UM, of course. Now, just to share a little bit, one of the 10-10 SDG, now this is something that is very, very new, whereby there's an integration of science, technology, and humanities to show results. So the 10 on 10, we've got the 10 science and technology drivers and 10 Malaysia socio-economic drivers that builds the horizontal and enabling the verticals in the ecosystem. Now, each science and technology driver should be exploring core technology and possible applications. And it is supposed to be driving fundamental and translational R&D. So this is something that we are moving into, guiding. It's a guiding tool to deep dive and serve as the base metrics for engagements with all relevant ministries, agencies, industries, and researchers towards identifying national niche areas. I'm going to share with you, I've got a few more minutes, I'm going to share with you a few examples. This is a research that was carried out by Matthews et al. In University of Manchester and his colleagues. It's published in Nature Research 2019. So when looking at collaborative, this is a specific example on the study on to look at bio-based nylon scenarios compared to fossil-based nylon. So before embarking upon the research that is supported by the Biotech and Biological Science Research Council UK and also Engineering and Physical Science Research Council UK, this is a work carried out with an industry, Zymergen Inc. So they did an overview of the constructive sustainability assessment process undertaken. They undertook an overview of they undertook a constructive sustainability assessment. And And this is an overview there. Now, what it does is the intention of the CSA process is to open up options, build capacities in anticipation, reflectivity and responsiveness for the future. So before they embark upon a research, they actually have the inputs and what will be the outcomes, looking at formulation within 1 month, evaluation, and also interpretation and follow-up visits and things like that. And the summary of the outcome of study as determined through analytical evaluation and deliberation interpretation, they have things like what would be the sustainability aspects of the outputs. They look at tackling climate change, which is SDG 15. Improving the health of global ecosystems, that addresses SDG 13 and 14. Eliminating poverty, hunger and poor health, that addresses SDG 1, 2, 3, 6, 7. And sustaining employment and economic growth, which addresses SDG 8, 9 and 11. So there are many things that, so this is something that we may want to look into when we, especially for the funders, our local funders, whereby we actually look at the big picture before we actually before our researchers actually embark upon certain important projects. Now, at the home front, of course, we do have different grants that are given out to the researchers, and also it's a very competitive grants. And for example, we have I'm just sharing with you one or two examples here. In this case, it's for food security, which is an LRGS grant MOHI. The general objective of this project is to enhance the competitiveness and sustainability of the Malaysian poultry, meat and egg industry. And the target deliverables will be poultry farming and processing in harmony with the environment. Production efficiency is at par with the world standards. Consumers are fully confident that local products are safe and wholesome. The poultry products achieve the standards accepted by importing countries. And if you look at the convergence of science, technology and social science disciplines that supports this research, this is something that we have to move into and move for. And perhaps if you look at each of these objectives very closely, some of it do address the SDGs as was reported by the earlier research. Another example is the project that looks into rehabilitation of Kim Kim River. This is also an example of what we're doing in Malaysia under the project University for Society with the Ministry of Science and Technology. And the collaboration is between several universities. As you can see, you've got also looking into the socio-economy and environment, conserve the nature, education, where we educate the population on how to love the nature and love river, smart river challenge, and also at the including the health aspect, where the introduction of psychological first aid guide was incorporated into the study. We can't move forward into the future without looking at the digital revolution and the rise of machines and artificial intelligence. So a key enabler of sustainable development in the coming years will be digital revolution, advances in artificial intelligence, connectivity, digitization of information, additive manufacturing, virtual reality, machine learning, blockchains, etc., that are all very familiar to us now. Now, with automation and advances in artificial intelligence and robotics, many more workers, even those who are highly skilled, may find their jobs and earnings under threat. So in the digital age, Anthropocene humans will also start to transform themselves, enhancing cognitive and brain capacities. Now, humanity is actually moving towards new civilization thresholds. This is the this was a few years ago. We said it cannot happen that early on, but super intelligent and intelligent machines might even develop a life of their own with the capacity to harm human agents. The digital transformation calls for a comprehensive set of regulatory and normative frameworks, physical infrastructure, and digital systems. The essential priority should be to develop science, technology, and innovation roadmaps and write the principles of digital transformation for sustainable development and to follow those guidelines to the T. Now, what are the challenges? Our conference today coincide with the third MCO in Malaysia. Now, please, everybody stay home and keep safe. The crisis caused by COVID-19 has affected research and education in a variety of ways. As far as research on sustainable development is concerned, the lockdown has significantly disrupted the usual communication channels and, among other things, has led to the cancellation of meetings and long-planned events. It has also led to the delay in the delivery of research projects. There is a gap in the literature in regards to how global crisis influences sustainability research. Now, the COVID-19 pandemic shows that sustainable development goes beyond national strategies. Every individual needs to make health decisions that meet personal needs as well as the needs of the broader community. Now, again and again and again, use face masks, observe social distancing, self-quarantine, etc., etc. The 3 C's and the 3 W's. Such decisions can help to curb transmission and reduce illness, death, and economic impacts. Now, a common basic understanding of environmental ethics and behavioral change at all levels are needed to ensure that protection of the natural foundation of life becomes a major consideration in all political, scientific, and individual actions. With that, I would like to thank you very much. It's the end of my keynote for today. Thank you.
Thank you, Prof. Maha, for that very illuminating and profound address on building sustainable science. And of course, it doesn't come without challenges, and how sustainable science is very important in order for us to achieve all the 17 SDG goals. So with that, ladies and gentlemen, please join me in thanking Prof. Raha for her keynote address. Thank you very much, Prof. Raha. So we cannot clap. I mean, I will clap. I have to ask everybody to unmute your microphone and give the Prof. Raha a big clap, a round of applause. Okay, then, Prof. Raha.
Yes,
See you soon and stay safe.
Yeah, you too. Take care.
Okay, thank you. Ladies and gentlemen, we now come to the technical talks. And our first technical talk is by Mr. Jonathan Han Wei Lim from ESCO Micro Sdn Bhd. Okay, Mr. Jonathan Lim is a Bachelor of Bioengineering graduate from Nanyang Technical University, and as a bioprocess scientist in ESCO Ester Singapore, he has been involved in the optimization of mesenchymal stromal cell expansion in tight motion TM bioreactors and the development of industrialized cell processing with bioprocess controls. He has also represented ESCO Ester to present scientific data at various international conferences such as the National Society for Cell and Gene Therapy Conference in 2020 and 2021. Ladies and gentlemen, please welcome Mr. Jonathan Lim. He will be speaking on large-scale 3D bioreactor technology linear scale-up of mesenchymal stromal cell expansion with tight XLTM system. With Jonathan, you are given 50 minutes to deliver your talk, and a bell will be rang 5 minutes before time. I hope you can hear it. So there will be a Q&A if time permits at the end of the technical talks. Jonathan, the screen is all yours. Are you speaking? I can't hear you.
Hi, can you hear me now?
Oh, yes, I can hear you better now.
Apologies. Okay, I'll start again. Thank you, everyone, and good morning. A moment. And good morning, everyone, and to the Malaysians, selamat pagi. I'm Jonathan Lim, Bioprocess Scientist from ESCO Ester, the research division of ESCO in Singapore. I'd like to thank the ICMBB organizers for the coordination of this event. It's not easy with the current COVID situation, and for giving me this great opportunity to share about the topic of scaling up of mesenchymal stromal cell culture and bioreactors. All right, so in the past 2 decades or so, a fair amount of effort has been directed to the exploration of mesenchymal stromal cells, or MSCs, for use in clinical therapy. MSCs are essentially multipotent cells that are isolated from various connective tissue all over the human body. They were initially thought to be an easily obtainable source of adult stem cells for directed differentiation to be used for injured tissue replacement. But over time, the value of MSCs has been found to lie less with their differentiation ability, more so in their secretions, such as proteins or exosomes. They have a unique ability, because of this, to exert various effects on the neighboring or co-cultured cells, both in vivo and in vitro. And this makes them very feasible for clinical use because they have a very good safety track record due to their immune privilege status. So while MSCs can be isolated from a wide range of adult tissues, the isolated cells are almost never sufficient for an average single dose of treatment. And this is definitely insufficient when we talk about allogenic treatment scales. So allogenic treatment scales is when you have a same set of cells that are administered to a wide range of audience and not just a single patient. So while there is the demand for large quantities of MSCs, the expansion and growth can be very laborious, especially when you're talking about trying to obtain billions of cells using cultural vessels like food flasks. Fortunately, bioreactors in the market to speeding up the process to make obtaining large numbers of MSCs more convenient. So with tight motion bioreactors specifically, different sizes are available depending on the number of cells desired to scale up to. The cells are seeded into the PEG bed. I'm not sure if you can see my mouse. PEG bed containing BioNOC2 carriers, that's just what we call them, and they are seen here. Each carrier is sort of rice size and is actually a mesh of polyethylene terephthalate fibers. So visually, with the cells growing on the carriers and staying with various dyes indicated here, the carriers look like this with 10 times magnification. And for the bioreactors themselves, we have two on display here. The cell cradle with its associated harvester, the cell shaker, is an intermediate sized benchtop bioreactor and is suitable for autologous scales of cells, so usually to one patient. But the type XL with the associated type XL cell harvesting system, or I will refer to it as XLHS, is larger and more suited for allogenic production sizes. So the premise of tight motion technology is shown here with the cell cradle, the intermediate sized one, is the tight-like cyclical alternating of the submersion and exposure of the PEG bed. So the PEG bed is over here, this box. And so this submersion exposure in media and air provides nutrients with the media submersion and oxygenation when exposed to the air. And then the slow movement and pumping of the bellows that pushes the media up basically provides a very low shear stress, especially when we scale up to really, really large PEG bed volume. So the larger the scale that you go to, usually you face high shear stress, but in this case, it's still okay. So while trying to obtain large volumes of cells, a series of back-to-back cell expansions is usually performed. You know, when you try to get a lot of cells for manufacturing. And so after each expansion, the cells will increase exponentially. So we performed an experimental setup similar to this concept, where such 4 cells were thawed into these flasks. Then they were passaged and seeded into the cell cradle. And then after that, harvested and seeded into the tight cell. And then correspondingly, the cell cradles that we tested had 0.1 liter packed bed volume. So that is the volume of the carriers in total. And then the tight cell had 1 liter of this, so 10 times more. Okay, so when we fast forward past the cell thaw and T-flask expansion, because those are just standard in MS culture, when we look at the cell cradle expansion itself, 20 million cells were seeded per cell cradle, and 3 cell cradles were seeded in total. So each cell cradle, 3 cell cradles seeded in the total, and each containing 0.1 liters of the packed bed. So 4 days later, an average of 154 million cells were harvested from each cell cradle. And if you take a look at the growth curve graph, the cells are harvested in the middle of exponential phase, and the corresponding media growth curve, media glucose levels indicate that the cells had sufficient media during this growth period. And these pictures over here were taken at 4 times magnification and show the gradual increase of the cells growing in the carriers through the culture period. And so after the cells had grown in the cell cradle, we have to get them off. So cell shaker was used for that. We harvested the cell cradle. And an estimate efficiency of 93.6% was obtained when we compared the harvest from the cell cradle to an extrapolated estimate of 10 carriers. So basically what happens is that these 10 carriers, manual physical flicking is performed instead of the cell shaker agitation. And all of this is performed, all of this is performed after enzymatic trypsinization. So it's similar to your passaging process in your tea flask where you do a rinse, and then you treat with your enzymes, and then you might tap it a little bit. So it's very similar. Okay, so after that, after harvesting the cells with the cell shaker, the cells were seeded directly into the type X cell, which had the 1 liter volume packed bed, and 250 million cells were seeded. After 7 days, 1.89 billion cells were harvested. And when we look at the growth curve, the cells were harvested just as they were entering the phase. The type XL measured pH readings also show that the internal measurements from the type XL so that the pH readings stay just nicely within the optimal ideal MSC culture range. And also it shows that the chamber CO2 compensating on day 5 onwards to counteract this acidity in the media. Also visually, when you take a look at the cells, the stains in the carriers, they're seen to increase in density through the culture period. So now when we talk about the harvesting of the type XL, the TXLHS, it's the same process as well as with the cell cradle. 97.7% harvest efficiency was achieved when compared with that small sample. But an unfortunate issue of this large volume of cell suspension, especially after rinsing the packed bed, because it's quite a large volume, is the cell loss from centrifugation. So the table values here do reflect a little bit of cell loss. But then we do have the FDA stains to demonstrate at least that the TXLHS agitation is efficient in getting the cells off after the rinses. To show that these cells are remaining on the carriers after. So now when it comes to MSC requirements, 3 basic quality criteria must be fulfilled. And the criteria laid out by the International Society for Cell and Gene Therapy, or ISCT, and being adherent cells, they have to remain plastic adherent. So they basically have to be able to adhere to your standard culture flask surface. They also need to express certain surface markers while lacking expression in others, so the long chain of CD. And also they need to be able to undergo trilinear differentiation into osteoblasts, adipocytes, and chondroblasts, so cartilage, fat, and bone. And so recently it's been thought that these 3 basic criteria have been a little bit lacking, and it's become ever so more important to perform functional assays in addition to 3 tests. So these functional assays will basically demonstrate the therapeutic efficacy of the MSCs when they are administered for their end clinical goal. So regardless of what they're going to be used, some functional assays should ideally be tested to kind of prove that the cells can go about achieving their intended goals. So examples of this can be protein analysis of relevant proteins or exosomes if, say, the conditioned media from MSCs is going to be used for therapy, or T cell suppression assays if the cells are going to be used for immunosuppression or immunomodulation effects. So the next few slides are just testings performed the cells harvested from the type X cell after the entire seed train process from T flask through the cell cradle through the type cell, the cells after that. At this point, they are Passage 7. So as far as MSCs are concerned, this is quite old already. But of course, if you start the seed train process with younger cells, then you get younger cells after that. So from these pictures, the tested cells still maintain their ability to adhere to plastic surfaces when plated immediately after the TXLHS harvest and after being frozen for 1 month, then thawed after. When we take a look at trilinear differentiation, the cells were adequate in performing the trilinear differentiation into the 3 pathways. And also 98.5% of the cells expressed the correct combination of surface markers when we tested them with flow cytometry. So this is quite good. And for more specialized functional assays, T cell suppression as a measure of the MSC's immunosuppression ability was tested to be an average of 53.2%. So how this assay functions is that various ratios of CFSE labeled PBMCs were co-cultured with the MSCs, and then anti-CD3 and CD28 beads were added to stimulate the T cell proliferation. So because of the CFSE fluorescence, the new generations of T cells would be identifiable via flow cytometry, and they can be selected for. And the corresponding suppression rates of T cell growth can be calculated for each ratio of PBMCs and MSCs co-cultured together. So another functional assay involving immunosuppression is IDO testing. So IDO, or indoamine 2,3-deoxygenase, is an MSC-secreted enzyme that suppresses natural killer and T cells. So plated MSCs were stimulated with different amounts of interferon gamma, and it causes them to secrete this IDO enzyme. And so the IDO secreting cells and the amount of IDO secreted was measured. And all in all, these secreted IDO values sort of suggest that the cells will probably have immunosuppression effect for use when administered in therapy. So in summary, both the bioreactors and cell harvesters function suitably for the scaling up of MSC culture, and the cells having gone through a seed train process with both bioreactors and series still fulfill minimum ISCT criteria and show potential immunosuppression ability with the functional assays. And so to end, I'd like to thank my fellow MSc research team members over at SYSTER. We are, as you can see, quite a small team, but the mutual support and various strengths the individuals bring to the table throughout this project has made it very enjoyable and satisfactory. So once again, on behalf of ESCO, I'd like to thank the ICMBB organizers for inviting us to speak and for organizing this conference. And also to all of you for all your time and attention. It's still a little bit early in the morning. Thank you very much.
Thank you very much, Jonathan. Can we see your face so that we can take a photograph at least? Thank you. Where are you? Oh, there you are. Okay. All right.
Yeah.
Okay. All right. Maybe you can move back a bit. All right. Okay. All right, Jonathan, Mr. Jonathan Lim, thank you for sharing with us, on the latest on 3D bioreactor. So if we have time at the end of the second talk, I will, if you have question, post it. If we have time, we will, answer your question. And if we don't, you can email Jonathan. And if Jonathan, you could just put your email in the chat box. That will be useful.
Yeah.
Okay, then our next talk is by our last talk. In fact, our last technical talk will be delivered by Dr. Zui Kian from Research Instrument. Dr. Zui Kian is the Director of Marketing Asia Pacific with PacBio. Prior joining PacBio, he was Director of Sales, Single Cell Proteomics for Asia Pacific with Fluidigm Corporation. Before Fluidigm, he worked for PacBio in various capacities ranging from application support in the US to sales channel management in China for 3 years. Before starting his commercial career in the sequencing industry, Dr. Zui spent 10 years at Affymetrix in the range of management roles, first in R&D and later on in field support and field marketing in Asia Pacific. Before joining Affymetrix, he led team leader of position at companies such as AlphaGene Inc. and Genome Therapeutics, now known as Agent Court, working on microarray application in the field of drug discovery. Dr. Zui Kian was a Life Sciences Research Foundation postdoctoral fellow with the 2017 Nobel laureate Michael Robesch at Howard Hughes Medical Institute. He received his PhD degree from Rutgers University in the field of molecular genetics and microbiology. Ladies and gentlemen, please welcome Dr. Zui Kian with his talk entitled PacBio Hi-Fi Sequencing Sustainable Technology for Sustainable Science. So Dr. Zui Kian, the screen is all yours. Again, you are given 15 minutes to deliver your talk and a bell will be rang 5 minutes before time. Thank you.
All right, excellent. Thank you very much. Can you all hear me?
Yes, I can.
Excellent. Okay.
Can hear and
you
see
my...
you as well. Yes, can you? I can see your slide and I can see you too.
Excellent. Thank you very much. Thanks to the meeting organizer for inviting us to give a presentation at this wonderful forum. I'm Zui. I'm actually working for PacBio and I'm the marketing director for Asia Pacific region. Okay, so let me put this in presentation mode. Okay. All right. So I'm going to talk about PacBio Hi-Fi sequencing, and this is my agenda for today. I'm going to start off with describing to you what is Hi-Fi sequencing, and then I will dive into 3 different application areas that are related perhaps to this audience. Right. One is in the human disease area, and next on the agricultural genome sequencing, and lastly touch upon the infectious disease microbial sequencing related to medical as well as the industrial settings. Right. So what is the Hi-Fi sequencing technology? Right. So I wanted to actually make that my first slide for you so you understand exactly what we're talking about. So Hi-Fi sequencing is actually a revolutionary sequencing technology invented by PacBio. And so right in front of you, what you're looking at is a long and accurate sequencing read that's produced from our sequencer. And for this particular read, you can see that the read length is about close to 20 kb, and that's extremely long, right? So, and if you look at the accuracy of this read, it is actually extremely accurate. As you can see, it's greater than 99.9% accurate. And so what that means is that along this 20,000 base sequence reads, we only have about 8 errors, right? So just to put things in perspective, what you see on the top, highlighted in this yellow bar here, is what the traditional called NGS technology read is actually going to be. Okay, so that's about the typical read length for NGS technology. So you can see that the Hi-Fi reads from PacBio is about 100 times longer than the NGS technology. So for some of you actually use the NGS technology, you can immediately appreciate what we actually brought to you, right? So this is extremely long and extremely accurate technology. So you can do a lot of things that the NGS technology couldn't imagine to do. So with the center of the Hi-Fi reads, produced by the sequencing technology itself, we enable you to do a lot of different applications. For example, you can do de novo analysis, sequencing analysis. You can do variant detection, right? So if the goal is actually sequence the genome and find out what are the mutations in the genome, and also you can do the targeted sequencing, just zooming onto a particular region of the genome, not the whole genome, right? If that's not what you want. And you can also do full-length RNA sequencing, looking at a full-length transcriptome, and lastly to look at the very complicated metagenome populations. So all these different application areas are now enabled by the hi-fi reads. Oh, that's exciting. So I'm going to tell you a little bit about the accuracy side.
Dr. Kian, we can't hear you now. We can't hear you. Dr. Kian, can you hear me? Dr. Kian, can you unmute your microphone? Hello?
Hello?
Hello,
Can you
yes.
hear?
Yeah, I
All
can't
right.
hear you just now. I think you accidentally muted your phone.
Oh, okay. Sorry about that.
Okay.
So let me redo this again. Sorry about that. Okay, so I'm going to describe to you about the accuracy. And here, what you see here is the three different technologies you were comparing accuracy. You can see it on the far right are the two different sequencing, highly accurate sequencing technology. One is the PacBio Hi-Fi, the other one is the NGS Illumina. You can see these two technologies are extremely high accuracy, right? Whereas the other technology called the Oxford Nanopore with a relatively poor accuracy. So you can see that the Hi-Fi read is extremely powerful in this regard. And with that, bring a lot of the interesting features for the technology, right? So you can, with that accuracy, you can actually get a very even coverage of the genome. You can get a complete genome sequencing and a allele resolution to get a very high allele resolution, and then also face the variants across the long range, and then you can get the best performance for all the different variant classes in terms of detectability. And then lastly, you can also do full-length RNA transcriptome analysis. So this was actually a result coming from the US initiative called the Precision FDA Challenge, in which they actually compare the three different technologies and then see which technology actually gives the least amount of errors across an entire human genome. And you can see that Hi-Fi technology actually gives the best results. So the focus right now for the technology in the scientific community is the sequencing of the human genome to look at the rare disease and the Mendelian disease and to figure out what are the detrimental mutations that can explain the genetic phenotype. So that's one of the focus for the PacBio company right now. And so I'm going to just tell you that there's a lot of international consortium efforts right now focused on using this particular technology to look at the rare disease in particular. So I highlighted in these red frame are three examples. One is from the Children's Mercy Hospital in the US, and the next is the Red Bull University from Netherlands, and then lastly is the City University of Yokohama. So I'm going to show you a few examples came out of the the efforts from these three different universities. So the first one is a team led by a number of researchers at the Children's Mercy Hospital. This is actually an initiative called the Genome Answers for Kids, in which they actually sequenced 100 rare disease samples previously not resolved by the NGS technology. So shown here in one particular example, you can see that this particular family with some kids suffering from seizures and ataxia problem that were not explained by the NGS technology. And after they use the PacBio long-read HiFi technology, you can see that they can actually identify the cause of mutations right in the middle of the START7 gene, right? So it turns out that there is actually a long stretch of repeat expansions, which explains the phenotypic, phenotype exhibited by the patient sample. The next one is actually a piece of work done by the researchers at Yokohama City University, where they looked at a young girl with a syndromic intellectual disability problem, and also the NGS was not able to resolve the phenotype. And so after they applied the long-read technology from PacBio, they were able to identify a very long inversion, about 12 kb, that is actually exhibited in one of the parents' DNA that's inherited to the kid. And then this again, shows the power of the long-read technology to solve some of these causative mutations undetected by the NGS technology. And this last example I want to show you is actually a very rare brain tumor that's called ATART. Okay, that's the full name, atypical teratoid rhabdoid tumor. And this particular kid, again, after many, many years of the diagnostic odyssey, was not able to actually explain the disease phenotype by NGS technology. But after they applied the long-range sequencing technology from PacBio, and they were able to identify there was actually a tragic insertion into this particular gene called a SMARCB1, and that leads to the splice defect for this particular gene. Again, offers a very, very good explanation for the phenotype. So now we can confidently say that with the HiFi technology, we offered additional technology innovations on top of what's known as the karyotype or microarray technology or the short-read sequencing technology in terms of the solve rate. Okay, so you can see as the technology evolves, the solve rate has gradually increased, and now we can actually increase that solve rates up to 70, almost 70%. On top of what people can typically get from the NGS technology, which sits at about 40%. So again, this basically shows the extreme powerful technology from PacBio in increasing the solve rates of rare disease. So this basically means that the HiFi read technology can help to end the diagnostic odyssey for many of the unanswered rare disease cases, because it can actually allow you to encompass the detection of all these different types of variants in one go. So not only we can actually have a great application in the human disease detection area, this technology also sees a lot of application in the plant and animal field. So showing in this particular slide a number of large international consortium efforts focusing on sequencing a lot of these plant and animal genomes. For example, Earth Biogenome Project, VGP, Darwin Tree of Life, so on and so forth. And so I'm going to show you one particular example coming from a group at Corteva, which is a subsidiary of DuPont, DuPont, and Kevin Fengler is the team leader over there. And in their hands, the goal is actually to use PacBio sequencing to sequence a lot of these plant genomes, right? Because they want to actually increase the crops' beneficiary features. So they wanted to actually figure out, what are the genomic makeup of all these different crops, right? So HiFi genome sequencing is actually a wonderful tool for them. And this just lists a number of practical benefits utilizing HiFi in their mind, right? So the first thing is actually because the HiFi sequencing is so accurate, right? So that means you need a very, very low computational demand on analyzing these HiFi reads. And also you can actually get end-to-end assembly with the dark regions in between. So you solve a lot of those previously unsolved areas within the genome by short-read and NGS technology. And lastly, they believe that there's no need for NGS technology to actually help the long-read technology anymore, because the long-read technology now is so accurate. And this slide basically shows that you can see that there's a lot of different plant genomes all being sequenced by the HiFi technology. from very, very long, big genomes like a wheat down to these relatively small genomes, right? And you can see on the right-hand side here, it shows the assembly time offered by these HiFi arrays are being extremely fast. You can basically finish the genome analysis in a few hours, which is unheard of before when you're running these NGS short-read technologies. And so this slide basically shows a comparison of many of the maize genomes, right? So they looked at the 19 different maize genomes in this view called a tag dot. Basically do a pairwise comparison of all different lines, right? You can see immediately one of the chromosomes, chromosome 2, there is a large inverted, region that were previously eluded many of the, research efforts. And as it turns out, that this particular area, nobody actually knows there's actually a large inversion on chromosome 2 that occupies about 30% of the genome of the entire chromosome, right? So you can imagine if you want to introgress a certain trait into this area, that's going to cause a problem. So to correct this particular inversion, they actually went ahead and used the CRISPR-Cas9 approach to actually flip this inversion back to its normal form. And now they're actually further characterizing this particular line. So what I'm trying to show here is that using the HiFi technology, you can actually immediately see the structural variants in many of these pan genomes. And that gives you the very, very clear view of what the potential problems or beneficial features in the genome. Also, there's a paper published in shrimp, right? In this particular case, scientists were looking at the transcriptome related to innate immunity system for the shrimp. And so they actually identified a lot of the brand new novel transcript that is actually intimately related to enhancing the immune system of the shrimp. So for the last remaining few minutes, I'm going to talk about this, microbial area. Basically, the most contemporary topic nowadays on top of everybody's mind is SARS-CoV-2, right? So this particular paper just published recently, the scientists are basically looking at the diversity of the SARS-CoV genome in the region of the spike protein, right? So what they're trying to do is to see whether you actually have the quasi-species within a particular clinical sample, and we know that the quasi-species basically represents many different variants, haplotypes, right? So in order to actually figure out all these different long-range phasing information of the SNP marks, you need to actually have the long-range and accurate sequencing technology, and the PacBio HiFi is perfect fit for that, right? So in order to do that, they actually sequence the long amplicon region encompassing S, E, and M proteins, right? So that's basically a 5.8 kb target that's being sequenced. So very interestingly, they identified many interesting quasi-species in one of the patient samples that corresponds to the viral load spike, okay? And that's what happens that this also coincident with the high anti-serum binding capability of the antibody within that particular patient samples. And interestingly, what they found was that, at day 15 after the onset of the disease, they found a lot of variants actually in the N-terminal domain of the spike protein started to pop up, right? There are 4 distinct haplotypes within this particular patient samples at day 15. And those variants actually in the NTD domain actually corresponds to the epitope region that were targeted by the antibody, right? So the researcher basically concluded that this particular research exhibited a capacity for the rapid genetic adaptation that becomes detectable in vivo with the onset of the humoral immunity, with the potential to actually contribute to delayed virologic clearance in the acute setting. So this actually offers a wonderful platform to detect those potential variants that actually can escape the immune response of the antibody. So I just want to quickly touch upon the metagenome analysis front for the HiFi application. So shown here is a generic sequencing through the 16S, microbial 16S gene, right? So with a long range capability, we can actually sequence the full length of the 16S plus additional ITS sequence information. So what this allows us to do is to actually identify those, microbial genomes down to the species and sometimes to the strain level, right? So this is actually a stark comparison with this other sequencing technology, where they can only look at the genus level or family level because they don't have the sequence accuracy that's afforded by the HiFi technology. So you can see that, just using E. coli as one example, with the strain ID detecting technology afforded by PacBio and then the Shoreline Bio, our collaborator, we can actually detect 100% of the E. coli strain, 100% of the E. coli strain, whereas if these other partial sequencing of the 16S can only detect a portion of the E. coli strains. So just to give you one.
Sorry, Dr. Ken, your time is up. If you could wrap up.
Yeah, sure. So just quickly go through this insect example. So mosquito, the scientists actually identified there's a number of strains that actually can render the mosquito resistant to certain drugs. And this particular example was recently published by a group at Macquarie University, where they actually showed that in the human gut the human gut immunotherapy, as it turns out, certain microbes also influence the efficacy of the PD-1, PD-L1 immunotherapy. So because I'm out of time, I just want to draw your attention to this last slide. Right now, we're offering a free smart grant competition. So if you are actually interested in clinical sequencing using PacBio, you are invited to actually apply. Submit your proposal to apply for this grant. So we're going to offer you 6 smart cells to sequence your sample free of charge. And the deadline is June 11th. So still have a few days left. So I highly encourage you to apply if you're interested. And this is where you actually can apply for this particular grant. So thank you very much for your attention.
Thank you, Dr. Zue, for sharing with us on a PacBio HiFi sequencing technology. And of course, I think those who are interested in applying for the grant, this is a very good opportunity for you to do so. Ladies and gentlemen, okay, since we are pressed for time, there will be no Q&A session, but if you have any question for Mr. Lim or for Dr. Kian, you can email them, and Mr. Lim and Dr. Kian, if you could leave your email address in the chat box so that participant can email you for questions. Thank you. Ladies and gentlemen, with that, we come to the end of our opening ceremony keynote. So our next session is the concurrent session, which will be in this hall 1, okay, and hall 2. So the hall we are in now is hall 1. So the session in hall 1 will be on agriculture and aquaculture biotechnology and molecular biology, and in hall 2 will be on medical biotechnology and molecular biology. To move to the other hall, you have to click on the link in the program, and you can move in, and you automatically will enter a waiting room and then will be admitted immediately. So let me see the time. So we will start in 5 minutes. So the concurrent session will begin according to my time at 10:38. Okay, see you all there. Thank you.
Hello, good morning, everyone. Sound
Okay,
check. Sound check.
right.
Can you hear me, Dr. Hannah?
Okay, yes, I'm here.
Can
All
you hear
right,
me, Dr.
okay, we
Hannah?
can start, right? Okay, everybody, welcome back to Hall 1 for the concurrent session on agriculture and aquaculture, biotechnology, and molecular biology. So this session, the session this morning will be chaired by Dr. Crystal Lim Siu Ping, and I think she's here now. So Crystal, the screen the screen is yours.
The screen, the mic, the
The mic,
speakers,
everything
and
is
the
yours.
platform
Yes.
is mine.
Yeah.
And soon will be Professor Jennifer. Thank you very much, Dr. Hannah, for the emceeing. And welcome everyone to Hall 1 of the 4th International Conference on Molecular Biology and Biotechnology 2021, or ICMBB 2021. It is an honor to have everyone here today, this morning, this wonderful sunny morning. And it is a greater honor for us to have as our plenary speaker for today in this session, Professor Dr. Jennifer Ann Hari Krishna, who is the director for the Center for Research in Biotechnology for Agriculture, also known as CEBA. She's also a professor of genetics and molecular biology and the Faculty of Science, University of Malaya, Malaysia. So Professor Jennifer is an award-winning researcher, a top researcher. Her list of awards is so multiple that I shall not waste too much time today to list her awards. Okay, it is all on the website. Feel free to look through her multiple awards there, and also in her own personal website, I think. And we'll give more time to Prof. Jennifer to tell you about her top title, which is "It's Not in Our DNA: Non-Transformative Gene Silencing in Orchids." Wow. Prof. Jennifer, you ready to start?
Thank you, Crystal, for the nice introduction. And yes, I'm ready to go. Can everybody hear me okay?
Yes, we can hear you and we can see your slides.
Okay, so let me just get a pointer and we'll be off.
Okay,
So,
sorry, Prof. May I just also remind everyone that if you have any questions, please type it in the chat, because we'll have a Q&A session at the end of the morning session, which is at about 12:10. All right, so do reserve your questions in the chat then. Thank you so much. Prof. Jenny, now it's to you.
Thank you. And thanks, Crystal, and also thanks to the committee for all the hard work putting this meeting together and for giving me the opportunity to share some of our work from CEBA University Malaya today. And I just wanted to have a slightly different title by saying it's not in our DNA, because this talk is, of course, there is some DNA involved, but we're actually interested in RNA and specifically in non-transformative gene silencing and in orchids. So I'll just give you a brief overview. So just to tell you, it's not all about DNA. RNA has emerged as a really important molecule, and we are especially interested in RNA silencing. So I'll give a little bit of an introduction to that, and then what I mean by non-transformative double-stranded RNA technology. And the examples will be some work we've been doing with orchids. And one study was for plant protection and another one towards novel flowers. So I actually borrowed this diagram from Dr. David, who's speaking after me, because I like it so much. And it's just saying that in the flow of genetic information, it isn't all about DNA. And today I'm going to be talking about RNA, but of course it's also about proteins and metabolites. And the whole thing that we're interested in is what the phenotype, what actually happens at the end. So you could choose to study at many different levels. And this is also true for biotechnology. We have in our first generation of genetically modified plants, we focus on the DNA. But in the newer technologies, we can skip the DNA and go straight for RNA. And that's because RNA has all these other essential tasks related to how the DNA gets used. And in particular, it can affect the level of expression at a post-transcriptional level. And that's what I'm going to be focusing on today. It is actually also able to influence the transcription, but today I'm just focusing on post-transcriptional technology using RNA as a biotech tool. A couple of terms, because I'm going to talk about RNA silencing, and actually many of you may know RNAi, RNA interference. They are actually essentially the same thing. They are natural pathways by which multicellular organisms use RNA for regulation of other genes. And this can be, as I mentioned, at the level of transcription, but today I'll be focusing on the post-transcriptional gene silencing. And in fact, long before, as with many things in biology, long before we understood the mechanisms, we could see a phenomenon and even use it in a biotech way. So this was pointed out in a review by David Bolcom in 2004, RNA silencing in plants, which is an excellent introduction to the topic. And he referred to this paper back from 1928 by a scientist called Wingard, who noticed that if you infect plants with a mild strain of virus, such that the plant doesn't die, newly emerging leaves have recovered. They show no symptoms and in fact could not be reinfected with the same virus. So it could actually protect the plants. And this he was used in for many years in biotech as a cross protection method. If you have a mild strain of a virus and infect it, it can actually protect it from more severe strains of the same virus. And this recovery, this immunity of the young leaves wasn't understood, but in fact is a RNA silencing mechanism. So that tells us from long ago, viruses are actually really great targets for RNA silencing. And when we come to biotechnology, being able to regulate or control or decrease the level of viral infection is really important, and in plants, but also in humans. And we can use RNA silencing. And recently, of course, we've seen the emergence of RNA vaccines in the fight against COVID. So RNA is really coming out of the shadows. Now, in the first generations of transgenic plants or genetically modified plants, people altered the DNA, and sometimes with surprising effects. This paper made it to the front of Plant Cell. And the surprising effect here was what they did was add extra copies of a gene called chalcone synthase, which is one of the flavonoid pathway biosynthetic genes. And they fully expected that if you have more biosynthesis of pigment by adding more of the genes, you should get a more highly pigmented flower. But what in fact they found was they had these variegated flowers with white regions, some totally white flowers. Again, they didn't really understand what was going on. And they refer to this as co-suppression. But what we now know is they had accidentally triggered an RNA silencing pathway, so that the gene, instead of making more transcript, was actually decreasing the transcript and resulting in this reduced flower color. And the same phenomenon had been seen then in other plants and also in fungi, where it was called quelling at the time. So this tells us as biotechnologists that we can also use RNA silencing for endemic genes inside the plant. So we can use it against the viruses. We can also use it to regulate plant genes. So what is the mechanism? And in fact, there was a lot of work going on to seek for that. And in plants, actually, it was first discovered a little bit earlier than the Fire&Mello work, but there's no Nobel Prize in plants. So if you want to know the history in plants, you should read the work of David Bolcom and his group. And they showed that it's a double-stranded RNA that is a trigger for virus resistance and homology-dependent gene silencing, in fact, the co-suppression that the earlier work had shown. But what Fire&Mello did, and I would say to my undergraduates, this was really the clever thing about it, because they did an experiment, they were using antisense. It was already understood that if you put in a complementary sequence to the RNA that you wanted to regulate, it should form a double-stranded RNA that wouldn't be able to be accessible by ribosomes, and you should get less protein from that RNA. So you could use antisense RNA to silence genes. And in fact, the first genetically modified plant, Flavor Saver tomato, was an antisense construct. But what they did in their experiment, as a control, they put in double-stranded RNA. This wasn't expected to do very much, but in fact, they noticed that the double-stranded RNA triggered a much stronger silencing. Now, lots of people get strange results in experiments, but they went further. They went on to find out why is it, and that to prove reproducibly, it's double-stranded RNA. And now we know the pathway is that the cells recognize this as being something to be processed into short, interfering RNAs by RNase enzymes in the cell. And these then form a complex of proteins, the RNA-induced silencing complex, that target the complementary sequence and either degrade it or inhibit it from being translated. And so we can sequence specifically silence messenger RNAs of our choice. And so we can use this in biotech to silence genes. So this is just a summary of sort of the natural paths. We haven't invented something new in biotechnology as usual. We're just using something that nature already has, that plants and animals can recognize RNA from viruses, and in fact, even make their own hairpin double-stranded RNAs, microRNAs, to regulate other genes through RNA silencing pathways. So we can inhibit the translation or completely degrade the RNA and prevent a particular protein being made in a sequence-specific manner. So this was just some examples. We can then put in transgenes to make artificial microRNAs or artificial siRNAs to trigger these pathways. But the pathway is triggered for the post-transcriptional gene silencing actually in the cytoplasm. We don't need to change the DNA at all. And if we treat cells with double-stranded RNAs, they're able to take that up, able to recognize it and form the RNA-induced silencing complex and target the sequence-specific RNA target. And we can trigger that just by adding double-stranded RNA. And we have two choices. We could use double strands, or we can use a hairpin. So we can use a single strand that folds into a double-stranded structure like this, and each are equally effective at triggering this. It is post-transcriptional and it occurs in the cytoplasm. It never alters the DNA, so it's a transient effect, but it's specific and it's not a genetically modified plant or animal because you have just altered the post-transcriptional level. So we were thinking how we were excited by this technology. We saw the potential for biotech and we wondered what we should do. And I'm very fond of orchids. So we decided, let's see what we can do with orchids because it's a good target for biotechnology, especially the flowers. There's a demand for new orchid varieties. We need high quality and the breeding is quite a slow process. The other thing is that the industry, tissue cultures, and even hobbyists are quite used to using biotech. Tissue culture is commonly used. And so that indicates a willingness to look at biotech approaches. Also, the tissue culture does allow you to do genetic modification, but that's a lengthy and expensive process. And it may give some regulatory hurdles for your transgenic plants along the way. So could we do this by directly using double-stranded RNA? Now, the changes we can make are only silencing. So we can remove or reduce specific proteins in plants, including those expressed for viruses. So viruses were an obvious target, but maybe other genes that affect the phenotypes. And so we tested direct application of exogenous double-stranded RNA to trigger gene silencing. And we've done one set of experiments for virus control and a few others for novel flowers. So the target for the virus was this Cymbidium mosaic virus. It's a double-stranded RNA virus. It's found worldwide and it affects most genera of orchids. It's very widespread in Asia. And of course, we can see the damage to the leaves, but it also will cause bad quality flowers. So this is something that is not wanted. And the infected plants can't be cured or treated. They will have to be killed. And then normally new tissue cultured plants, which should be virus-free, will be introduced, but they will take several months to grow and flower. And this is a loss of income. It's also very transmissible by sap during the handling. And interestingly, it doesn't have an insect vector. So the infection is only when the plants are handled. So we figured it would be a useful target because when we're handling plants at the stage of transplant from tissue culture or even pruning, it should be possible to treat them with double-stranded RNA to protect them if we can get a double-stranded RNA that will stop the virus. So just to explain a bit about the virus, it's a double-stranded RNA inside a protein coat. It's the topomovirus type. And we decided to inhibit the coat protein because when the virus is in the cells, if it cannot make the coat protein, it can't assemble new particles and the infection will be stopped. So the idea is treat with double-stranded RNA with the sequence that is part of the coat protein of the virus. Treat that onto the plants. It should target and silence. And then we should see less virus because if it can't make the coat protein, we shouldn't get the virus made in the plants. So how are we going to make our RNA? Well, we went for a cheap and easy way, which was to use E. coli expression. And the first sets of experiments we did, we decided to do the fire and mellow way, which was to check sense and antisense as well as double-stranded. So we made, using T7 promoters in RNase deficient E. coli, we made one strand, the sense strand. In another strain, we made the antisense strand, and then we mixed those together to make the double-stranded RNA for our experiments. We use a strain called HT115, which is RNase deficient, so we can get lots of RNA. And we induce the T7 promoter with IPTG, so you get really high expression. If you run this stuff on a gel, you get one very strong band of the RNA that is your specific RNA. So most of the RNA you get out of the cell is actually the one you want. And we just use that crude lysate in our experiments. So then we got some seedlings, actually tissue cultured plants. And when we transplanted them, we treated them either with the sense or the antisense or the double-stranded, and challenged them with the Cymbidium mosaic virus. And then we did an assay 30 days later using PCR to the virus coat protein to see what we would find. So the first group is the normal virus infection on plants not treated with RNA. So this tells you the comparative level that you expect of the virus based on levels of coat protein. We can see that the plants treated with sense or antisense had decreased amounts of virus, and those treated with a double-stranded had effectively the same as the two groups that were not treated with virus. That is the complete control, not treated at all, and the control that was treated with a double-stranded RNA, but not the virus. So this showed that the treatment was very effective at preventing the virus disease. And we went on to publish, of course, and we also have patented, and we won a few awards for that. So having shown that it works well against virus, we wondered, could we also use it then to modify the flowers of the orchid? And so we thought this would be a more rapid way than expressing double-stranded RNA inside the plants and seeing what happened. We could actually maybe do more genes if we could just treat them with double-stranded RNA and look for phenotypes. So the first thing we had to decide is what genes should we target? So we looked at the flowering pathway and we noticed that many flower phenotype characteristics are actually influenced by a family of transcription factors called the MIB family. So they regulate genes in the anthocyanin biosynthesis pathway, the flavonoid biosynthesis pathway. They also regulate cell shape. But it's a very large family of transcription factors. So the first thing we had to do is identify which of the genes are likely to be involved in flowering in Dendrobium. So we did this using a phylogenetic approach. So there's one completely sequenced Dendrobium, and that is the Dendrobium catenatum. And we found 63 MIB gene sequences in that genome. We then translated all of these into proteins to do this comparison with those from Arabidopsis. And then the 37 other plant species, we just selected genes that are related to color and shape in flowers. And then from that, we identified the homologs from Dendrobium to clone and use for the double-stranded silencing. The next thing we had to do was characterize what a normal flower development looks like for the Dendrobium hybrid. And we did this together with Dr. Trudy from Leicester University. And this was staging the flowers at different stages of development and looking at the phenotypes so we could see exactly what a normal flower development looks like. So then the experiment. The idea is we've identified some genes that we think are involved in orchid flower development. We make the RNA using the bacterial cells as a double-stranded RNA. And then we use that in our experiments to treat the flower buds and see what phenotypes we get. Hopefully we see some silencing. Again, we'll use PCR to detect the level of messenger RNAs. And we'll just look at the phenotypes to see if there's any changes to the flowers. So the first gene we did was called MIB1. In fact, it was just the first MIB from Dendrobium hybrid, so we called it 1. There's no real convention on this. And we first of all checked that it is expressed during flower development. So this is the real-time PCR across different stages of flowers. And we can see, yes, it's expressed as the flowers develop, peaking just before the flower is fully mature. This time, we use a slightly different construct. So it has 2 T7 promoters. That means when we induce with IPTG, we'll get both strands of RNA synthesized. So then they should anneal, and we can have our double-stranded RNA. Again, because it's T7 and an RNase deficient strain, the majority of the RNA you get out of these cells after induction is the RNA that you want. Then we can treat the flower buds and look at the phenotypes as the flowers develop. So starting from around the early bud through to the open flower, which is about 30 days. And we actually have to stage them because in Dendrobium, you have several flowers on the stalk. So you start each of them at the bud and follow them through so that we can get all the replicates. We have replicates within a plant, replicates with different plants, and also the control treatment to compare. So just looking at the 5, 6, and 7, which is the later stages of bud development, and looking at, first of all, the RNA levels by RT-PCR, we can see in the control, we have much higher levels of RNA than in the double-stranded treated plants. So what this told us was our double-stranded RNA is reducing the amount of MIB RNA. But when we look at the flowers, so the arrow in each case is indicating the flower that has been treated with double-stranded RNA, we really couldn't see any difference. And this is also the case in the open flower. But we did know that some of these genes change cell shape. So we couldn't see any difference in color. We couldn't see any shape change in the flower. But when we looked at the cells of the flower, and first of all, again, we had to characterize all of those using electron microscopy. So we divided into different domains of the petals, sepals, and lips, looked at the structure and shapes of the normal cells before and after treatment. And what we found was that the only change was in the cells on the lips of the orchid. And so in the control, I hope you can see these are sort of more bumpy and pointy, or what we call pyramidal shape, conical, and these were much flatter after the treatment. If we look at the side again, we can see the more spiky and more dome shaped. So it was a reproducible difference, a measurable difference, but not visible to the human eye, which was a little bit disappointing, but it was good enough to publish. So that's something, and it was good enough for a master's thesis. This is the work of Su Yi. So we went on, we managed to get another grant. So we said, okay, now we've got some more money. Let's look at some others. So we characterized a few more genes. And this time we decided to not just do a transcription factor, but a structural gene. So if you remember, the chalcone synthase was the one that I described earlier, that when they silenced it, they got white segments in the petunia flowers. So we thought, let's see if we silence the chalcone synthase, can we also remove the purple color in our dendrobium flowers? So again, we're using the same vector as for MIB1. We have the chalcone synthase, MIB3, MIB4, and also our control is treating with the RNA from E. coli with the empty vector in. 5 flowers per plant, 9 plants per group, and at all these different stages, and then assess the phenotype. So here I'm showing you one row is one gene treatment. So this is the cell, the flowers treated with the double-stranded RNA to MIB3, this row with MIB4, this with chalcone synthase, and this with the empty vector. And what I hope you can see is, even to the naked eye, we can see that the normal color is much more intense than the treated flowers. Also, you may notice there are some differences in the shapes of the buds and also the shapes of the flowers. So yeah, I can tell you they look different, but of course for science, we need to count, we need to quantify, we need to do statistics. So we were learning as we went along. So we did some color assessment. And here, what we do is we measure the color intensity with a color hexa analysis and a colorimeter. And it is in 3 components: light to dark, red to green, yellow to blue. Each of those come up into a score, and then we can measure the difference. And in each case, we compare the control to each of the treatments to get a score of delta E. The bigger the delta E value, the more change there has been, so the more different the color. And so we saw that the biggest values changes were in the petals of DHMIB3 treatment and the sepals of DHMIB4 treatment. So if we look at that here, again, you see the petals, MIB3, sepals, MIB4, when we plot it as a graph. Now, I also told you, oh, sorry, I should mention that as well as looking at the levels of RNA, we could look at the concentrations of anthocyanins. And we also saw that they were reduced. So the blue columns are DHMIB3 treated, the orange is DHMIB4 treated, and the gray is the chalk-on synthase, the yellow is the control. You can see that actually the MIB treatments decrease the anthocyanin more than the chalk-on synthase. And we think these genes are probably further upstream at crucial places. So that means those transcription factors are affecting biosynthetic genes earlier in the biosynthetic pathway. I mentioned that the flower shapes look different. So I have many, but on the slide, I can only show you two for comparison. So this is an untreated flower, and this is a flower that was treated with the MIB4. And we actually take multiple flowers and we flatten the petals, the sepals, and the lips, and then we photograph them when they're flat. And then we use wireframe plots to outline the shapes. And we can do then an overlay and measure a distance between the two plots. So this again can quantitate the shape difference. And so this again, the taller the column, the bigger the shape distance. So the more the change has been. So I think you can agree that the sepal here and the petals here are quite different. But how do we quantify it? So we quantified it here using the wireframe plots. And you could see that the MIB3 and the MIB4 treatments do change the shapes of the floral organs. So this is quite exciting. Of course, we will probably need to test many more MIBs to get something that might be desirable by growers. But if you remember, we're not making any genetic modification. We are not changing the DNA. We're simply painting these flowers with RNA and getting these phenotypic changes. So I come to my summary. I hope I've convinced you that direct application of double-stranded RNA is a very useful biotech tool, and it can protect orchids against Cymbidium mosaic virus. And in fact, this is likely going to be the first commercial aspect, not in orchids, but for crop protection in other plants, especially viruses, but also several people have shown it to be effective against other pests and diseases. So just finding the right target, even for insect pests, has been quite successful in research level, and many companies are moving towards commercialization of this technology for field use. Again, no transgenic, just using the RNA as a treatment to protect your crop. We also found that we could alter the transcripts of the flowers. So one obvious use for researchers is that's a quick way to determine gene function. We don't have to make a genetic knockout. We don't have to do a transformation experiment, which could be very powerful in perennials and slow growing crops, that we can shortcut the steps to see what happens when we silence the gene. And it may have a potential for use in flower modification, again, avoiding having to do genetic modification. It's much more rapid and less expensive, so especially useful for functional studies. And of course, we are trying to do more testing for flowers, and also we are looking at virus protection in other plant species. So what's the future for this in biotech for agriculture? There's every indication that RNA sprays will be in the market as pesticides soon. And one of the issues or the challenges has been, how do we make the RNA stable? And lots of work on this. And one very famous one from UQ in University of Queensland is to use the bioclay nanosheets. Dr. Nina Mita has shown this works very well, and they're using that for crop protection in tomatoes in greenhouse, and I think they hope to commercialize that soon. We believe there's potential for use in floriculture, and probably it should be more acceptable to public because there's no GMO. The only issues will be for sorting out the regulations, as they can be a little bit unclear. But some countries have already established positions. Australia and New Zealand say for crop protection, they're not going to consider treating RNA as a GMO. They're going to treat it as a pesticide. So it will be regulated purely as a pesticide and not as a genetically modified organism. So before I go, lots of people to thank: ICMBB, the conference organizers, MSMBB, and all my friends there. Funding we had from Ministry of Education, FRGS grants, and FRG grants, and university grants. So several little bits of money here and there to do each of the projects. This was the hard work of 3 master students, principally, Teng Wei, Su Yi, and Muhammad Ashraf. And together, to help me supervise, Dr. Purabi, Prof. Yasmin, and Dr. Trudy from University of Leicester. Thank you very much.
Thank you, Professor Jennifer. Let's give her virtual claps. You can give virtual claps in the reaction emoji. Okay, that's what I'm doing right now. You do see that. Okay. Yeah, and I see that, oh, there's many claps, Prof. Jenny. Let's do.
Wow, thank you.
You have hit 21 claps now. Wow.
My friends must be here.
We should do a competition for saying which speakers have the most claps, huh? Okay, but that's wonderful, Prof. Jenny. I never knew that the lips of the orchids are so attractive, huh?
They are to insects.
They are to insects, yes. All right, so if anyone has any questions, please post it in the chat. Okay, no worries, just put your questions there, and also your name and your affiliation so that we can call out who asked the question later. And Prof. Jenny, may I invite you to please stay back later for the Q&A panel, which should run at about 12:10 p.m. later, all right? For about 15 to 20 minutes. So I'll see you again later, Prof. Jennifer. And thank you again for the wonderful talk on orchids, all right? And all right, so now we shall have the next speaker, who is our invited speaker for this session. And he is Dr. David Ross Appleton. He's the head of biotechnology and breeding, ICMBB Plantation, Group Research and Development, Malaysia. So I just briefly introduced Dr. David Ross Appleton. He obtained a PhD in chemistry from the University of Auckland, New Zealand, with experience in biotechnology and pharmaceutical research, as well as process engineering. So he came to Malaysia in 2008 on attachment to University of Malaya after working for 5 years for Malayan Pharmaceuticals in Singapore as a principal research scientist in drug discovery. So he went on to join ICMBB in 2010 and is currently the head of, as I mentioned earlier, the head of biotechnology and breeding in ICMBB Plantation R&D since 2015. So Dr. David will be telling us about moving genome select to the field, the highs and lows. Dr. David Appleton, the floor is yours.
Thank you very much. And thank you to the organizers for having me here today. Let me just share my screen.
Okay, great. We can see your screen.
All right. Oh, good.
Okay, you're good to go.
Great. So today I'm going to talk to you a bit about our genome select oil palm and the journey of getting that into the field and the many highs and lows along the way. So deforestation really is an urgent challenge for the world, in particular the agriculture industry. How can we feed a growing population and put a stop to deforestation at the same time? And the only way really is to increase the yield with the land that we have and produce more of what we have today. So in order to do this, we have to identify and optimize, and most importantly, scale technologies and breakthrough innovations that increase yield. And as we'll see later, this is not always trivial. In fact, it's never trivial. If we keep our eyes open along the way, we can learn from this process and improve further. So always keeping our sights on the end outcome that's needed, in particular, being able to apply things at a commercial scale. It means that things actually have to work. We have to understand the fundamentals. We have to understand how it works so that we know when it won't work. And things have to be able to make economic sense in some way and be at a sufficient scale to make a difference. I think teamwork in the end is really the defining factor. So it was a 12-year journey for us from 2016 when we first planted the commercial palms, as you can see here. But going back further to that, back in 2009 when we sequenced the oil palm genome. And now 12 years on, where we can see those palms actually fully grown and producing commercial yield. In fact, now even having genome select mother palms that are producing seeds. And this year in 2021, we're on track to produce about 1.5 million seeds for planting within Sandabi plantation. And we're also rolling out this technology in Papua New Guinea and Indonesia. And in fact, even applying it for all of the seeds that we produce to make sure that every seed we produce is pure, genetically pure and traceable. So this was clearly a high, but as I said before, there are many lows, and there's that constant feeling that success is just at the end of your fingertips, actually. So as I said, it all started with a reference sequence, a reference genome of just one palm, and of course that's not enough to do anything with. So we had to look at the variation across our populations, and we chose 59 different palms to represent all of the different breeding populations that we have in Sandabi plantation. And we had to pick out 132 in the end. That included a large number from our commercial seed production populations to be able to get a good representation of the different variation in Sandabi plantation. So from one genome sequence to 132, unfortunately, things got a whole lot cheaper in that time frame. But after doing all that resequencing, I guess we kind of got a shock when we saw that there were 7 million different SNPs that we found in these different backgrounds, which is, I think, more than any of us expected. And even after doing a large number of SNP filtering and filtering out those with a low minor allele frequency rate, we still had 600,000 really quality SNPs, which, as I said, was quite a shock. We thought to begin with that we'd be fine with producing an array of 60,000 SNPs for doing genotyping, and now all of a sudden we've got 600,000. And so how to choose them? So we thought that we would look at LD blocks, basically linkage disequilibrium blocks. And it became very quickly apparent that oil palm is not like annual crops. In fact, it's not like many of the other crops where they were doing micro-assisted breeding at the time. And the LD blocks are actually very small. So you have very short distances of the genome where there isn't a lot of recombination going on. So commercial populations, we saw LD blocks around 120 kilobase. But that was within one cross. And when you look at breeding populations, within a population, it was around 50 to 80. But between different populations, it very quickly dropped down to about 10 kb. So that basically meant that if we wanted to have one SNP at least per LD block across the whole genome, we were going to need 180,000 SNPs. So that was a big increase from the 60,000 that we first thought. So anyway, we decided that was the only way to go, really, is to make sure that there's at least one SNP representing every LD block across the genome on average. So then we started doing genotyping with our 200,000 SNPs. I say 180K because when you put it onto an Illumina array, you lose about 20,000. So we started doing this genotyping across different populations, and we saw quite a lot of clustering taking place, which again, I mean, now in hindsight, it's not a surprise, but at the time it was. You can see the wild populations clustered very distinctly away from the commercial populations, which is perhaps fair. But within the commercial populations, we could see very definite clusters of different breeding populations that came from different breeding stations or different backgrounds very slightly. And what we saw is when we developed sort of genomic selection models, the accuracy within a cluster may be quite high, maybe above 0.5 for yield, which is really good. But that quickly dropped to basically 0 if you wanted to look at a model across different populations. So again, that left us with this quandary of, so what do we do? Do we go deep within one population, or do we try and go very broad? At the end of the day, in a commercial setting, when you produce seeds and you have to produce millions of seeds, we kind of had no choice but to do both. And that required a really significant increase in budget. As I said, from 50 palms that we thought about sequencing to start with, it ended up at 132. And from 60,000 SNPs that we thought we would need, we ended up needing basically 200,000. And from 3,500 palms, it ended up to be 7,000 palms. So the budget was just going up and up and up. And this was around 2011. And we can remember frequently prostrating ourselves in front of the managing director of the company and pleading for more money. Fortunately, that we were in so deep that we had to continue on. And so we managed to get that money. In the end, we were able to develop some genomic selection models. We managed to select 1,000 of the the highest quality and best SNPs out of that 200,000 that are associated very strongly with yield. Total oil, of course, was very interesting to us, but also other traits like the oil to bunch ratio or the oil content within the mesocarp flesh, and a number of other sort of traits that the breeders would often select on. So we had these 1,000 SNPs, and we developed a genomic select model which had about 60% accuracy and would enable us to genotype a population of individual palms and select out the ones that would be in the top 30%. And that would give us about a 15% improvement in yield, is what we reckon. So we now kind of had a commercial model of how we could deploy this. We could genotype seedlings, and we could select the best of them out of the variation that was there. In fact, I should note that this histogram here is actually the variation in yield within a field of breeding commercial palms. So you can see that within commercial palms, there's a huge variation in yield from basically nothing all the way up to 12 tons of oil per hectare, with the average around 5 or 6. There's a lot of reasons for that spread. One, of course, is environment within the field even, but oil palm is still a relatively wild crop. It's about 25 years for a full breeding cycle. So in 80 years of breeding, we've only made our way through 4 or perhaps 5 cycles of breeding. So, right, we had a model on how to do this. We thought, okay, so what do we do now? We're at about 2014, early 2014 now. So we had a way of selecting for yield, and we were quite proud of that. But of course, the company said, well, you promised us 2016 you would have something commercial for us. So we started doing the maths on what does that mean. So a commercial field is at least 50 hectares in Sandavi plantation or in oil palm. And in order to just plant out 100 hectares, which is pretty small, still in the scheme of things, we were going to have to genotype 80,000 different seedlings. And it would, as I said, with 1,000 markers, that's 80 million data points. And we'd have to do that in a period of time from the seedlings reaching the nursery, when they're very small, to 12 months later when they get planted in the field. So we basically had 10 months to do that. So we thought, wow, heck, we better start doing this. So basically from having the first set of validated SNPs, we had about 5 months until we had to have everything ready. And we were able to purchase a high throughput genotyping system from LGC, a CASP system. And this could cope with that kind of capacity. And we managed to train the team up, and with a bit of insourcing and outsourcing, we got the lab up to speed so that by the end of that 10 months, we were genotyping everything in-house and doing our selection. So you can see in the nursery, all of the seedlings laid up there. But it was apparent very early on that sampling was going to be the problem. It's relatively straightforward if you have some money to go and buy a high throughput genotyping system, but you have to get samples to feed that, and then the samples exist in the nursery. So we tried a few different ways of doing it. We thought, okay, we could have this really nice system here where you go to the field and you have like a little hole punch that punches holes in the leaves into a little cassette that you take back to the lab, and it transfers these punched leaves into a 96 well plate that you can then put into your extraction and genotyping system. We tried this out to start with. It kind of worked okay, but in the end of the day, it didn't work because the oil palm leaves are quite fibrous, they're quite sappy, and we're doing this at 30 degrees temperature with a lot of humidity, and basically you have lots of issues with it jamming. So what we found is it would take you maybe sort of 3 or 4 hours in the morning to get through a decent batch of samples, and that was all in the heat. And then you would go back to the lab, and it would take 10 minutes to transfer from this cassette into a 96 well plate. But what we found in the end of the day, by far the best way is just to go to the nursery and cut the leaf, put it in a barcoded bag, and take that back to the lab. Whereas you could do all of your sampling within half an hour or 1 hour. And as long as you had a really nice system with barcodes, then you take it back to the lab, and you can use an analogous system to this, but it punches the leaves directly into a 96 well plate. So what this means is you spend much shorter time in the heat, using a very typical pair, well, basically a pair of scissors, no technology at all. And then it might take you 2 hours in the lab to do the punching, but you're with the aircon on and it's a nice system that you can clean and it doesn't have this problem of jamming and cross-contamination. So we managed to get through this one on the fly. So we made it to 2016, and I think this was definitely a high. In fact, it was such a high for some people that you can see when they threw their hats up in the air. One poor researcher threw her phone into the air as well. You can see that up there. And going from that time in 2016, just planted right in the middle of El Nino, to the palms growing, and then now today with lots of bunches and seeing fruit, that was definitely a high. But of course, 100 hectares, when we have 100,000 hectares in Sandabi plantation, is not really enough. And this model of sampling every single seedling and then genotyping all of the seeds and selecting the best to plant, whilst it was kind of commercially feasible, it was pretty borderline. It would cost around 8,000 ringgit per hectare to genotype the seedlings. And in order to plant 2 million high-yielding oil palm, you would have to genotype 6 million seeds and then throw away 4 million. So it's quite an expensive exercise. So we soon realized that we would need something a bit different to this, and perhaps the best way to do it is to genotype all of our mother palms and our pollen palms, and use basically a prediction, genomic select prediction method to see which were the best combinations in order to be able to produce those seeds directly. So basically you only have to genotype the parents in this case. In the end, the cost is very much considerably cheaper. It's about 50 to 100 ringgit per hectare, and that includes genotyping all of these seeds to make sure that they're pure and you can trace them back to the parents. So we're on track now with that. As I said, 1.5 million seeds this year, and we'll be selling seeds externally in another 2 years' time. So now it's 2021, and these palms were planted in 2016, the first ones anyway. And we got to look at the yield of these palms, which after 2 years after planting, you can start seeing bunches. It's called scout harvesting because it's pre-commercial yield. And we planted 2 fields actually at the time, both were 50 hectares. One was in an inland environment or inland environment, and the other one was in a coastal environment. Coastal environment, the yield tends to be better because there's more water, basically a higher water table, and the soil's better. But looking at the inland and coastal environment, both of them were pretty much on track, and these kind of yields are actually extremely good. It's what you would normally expect from a 1-year-old field, 1-year commercial field, not a pre-commercial field. So everything was looking pretty good. And then we started our commercial harvesting, which is starting at 3 years after planting. And we can see the coastal field continued picking up more and more yield. And in fact, it turned out to be the highest yielding first year field that we've ever had in Sandabi plantation. It was very good. It was basically out yielding all of the average fields in that plantation, despite them being very much mature. But the inland gave a different story. Basically, there was about 4 months of almost no yield at all. As you can see in the previous slide, yield was picking up nicely, but then there was no yield at all. But then the yield was okay again. So it was a bit of a surprise. I would say that was a bit of a low. But for us, I think the target really is that we need to be able to double yield by 2050 to be able to make the right contribution to the growing population that we have. We need double the amount of food by then, basically. So in order to be able to produce that extra field without deforestation or without increasing our planting size at all, we have to double our yield. So yield in one location is not good enough, and yield with 100 hectares or 50 hectares in a coastal field is not good enough. So we have to address this problem that I was just showing you, where the inland field wasn't producing very good yield. And it really comes down to this. It's this kind of performance challenge where one part is the genetic potential, and then you have a drop in yield because of suboptimal growing conditions, and then another drop in yield because of poor crop recovery, and then you end up realizing considerably less. So for example, in a breeding trial for oil palm, we have about maybe as much as 10 tons of oil per hectare yield, but our commercial fields only yield around 4.5 or 5. And so what remains to be seen is if we increase the genetic potential, will the realized potential also increase as well, or will this just stay the same as the genetic potential goes higher? I think in the end of the day, it's probably something in between, where if you were to increase the genetic potential by 20%, probably the realized yield will go up, but not by 20%, maybe much less. And of course, a lot of that is because of these other limiting factors. Unless what we can do is start selecting palms with genetic potential that address these growing conditions and harvesting, then maybe we can. A bit of a hint is if we look at all the genetic markers or SNPs that we have that are associated with total yield, only a quarter of them are actually also related to or associated with a trait that our breeders would normally select. So basically, 3/4 of the markers that we have for total yield, we have no idea what trait they're associated with. So going back to that field just now, I showed you where the yield was very poor for 4 months. That was an inland field. Of course, what happened in that time is a lot of very strange weather patterns and very dry seasons. And what we can do now with the help of digital technologies is we can go and census these palms. So here's the 54-hectare field. And these little points here are the palms that are suffering from stress in August. And by suffering with stress, we mean they're not producing any fruit at all. We come back in February and we can see that there's only a few palms in the whole field out of 9,000 that aren't producing bunches. So what we need to do now is we need to monitor this pattern and see actually what is the genetic component. Is this something that's random, or is it something that's very genetic, where there's a genetic response to stress that switches off fruit development or flower development, or maybe causes floral abortion in these palms? And then maybe we can start selecting for it. At the same time, we are developing genome select models using the same kind of technology for diseases like Ganoderma. In fact, now we're already starting to see very interesting QTL patterns between different populations that can guide us in our breeding to help breed palms which combine disease resistance from different populations. So we're quite fortunate, I guess, in Sayandavi plantation because, as I mentioned before, yield in one environment is not going to be good enough to help us to make a sizable impact on the world when it comes to food production. We have plantations in Malaysia and Indonesia and also Papua New Guinea, and we're now able to deploy this technology. In Malaysia, we have 3,500 hectares now planted across many different states and environments with Genome Select that we can start monitoring the yield and seeing how this can be further optimized in future. So just to reiterate, right, as I said, in order to realize this massive step in yield that we need, we really have to have breakthrough innovation. We have to increase yield, and yield is really the core of Sayandavi Plantation's growth story, to be able to have a deforestation-free industry. But we have to really address those issues, and not only that, we have to address other issues related to the industry like harvesting and the reliance on labor, and this kind of things like climate change and the impact it's going to have on yield. So in the company, we're putting all of this together now and trying to shift everything higher, not just the genetic potential, but also the realized yield. So thank you for listening to me, and I'm happy to take questions later on. Thanks.
All right, thank you, Dr. David Appleton. Again, let's give him virtual claps in the reaction button. All right, just click the clap button, and yes, I can see many claps coming in. Yeah, 21, 22. Oh, David, you have beat Prof. Jennifer in terms of virtual claps. Okay, again, Dr. David.
Thank you.
Thank you for the wonderful talk. It seems that there are more highs than lows in using Genome Select in the field of palm oil. All right, so may I also request you to remain later at the Q&A panel session, which should start about 12:10 or 12:15, about that. So I see you later, David. And everyone, again, if you have questions, please type it in the chat. Don't be shy, okay? So from now, we will have a 5-minute break. Please feel free to go grab a snack, grab a drink of water, go visit the washroom for about 5 minutes, and we'll be back at 11:37 Malaysian time. Again, reminder to post your questions in the chat. let's not leave our speakers with a questionless Q&A session later, yeah? All right, see you guys in a bit.
Puzzled by your sequencing results? You've seen the incomplete picture of short reads. You've seen the inaccuracies of traditional long reads. PacBio Hi-Fi sequencing gives you the whole picture. Hi-Fi reads combine the best of short reads and long reads to help you unlock the secrets of even the most complex genomes. Sound too good to be true? Go here to get the whole picture.
Good morning, everyone, and welcome back to Hall 1 of the first day of ICMBB 2021. So our next session to be continued is the oral presentation sessions, which I expect to have 4 oral presenters for this session. And we'll begin the oral presentation with Dr. Low Chen Fei, who is a research fellow at the Institute of Systems Biology, University Kebangsaan, Malaysia. And he will be presenting his research title, a research talk, entitled Attenuation of Macro Vacuum Rosenbergi Nodavirus through Codon Deoptimization of Virus Functional Genome. Wow. And I see a very big crayfish there, which makes us a bit hungry for lunch, right? Okay, so Dr. Low, can you turn on your camera if you don't mind?
Yeah, sure. Can you hear me?
Yes, we can hear you, see you, and see your slides.
All right, thanks.
So you're good to
Thank
go.
you,
You have
Dr.
about 10 minutes for your talk, yeah? All right, the floor is
All
yours.
right. Okay. Good morning, everyone. Thanks to the organizing committee for the opportunity for me to share some of my research findings on the attenuation of macrovacuum Rosenbergi nodavirus through the codon deoptimization of viral function and genome. So a bit of introduction of the host species. The species actually inhabits both fresh and brackish water, and the adult prawn can grow up to approximately 32 centimeter for the male and 25 centimeter for the female, which is among the biggest size of the crustacean. And the aquaculture origin of this species in Malaysia starts in 1960s when it was discovered by the FAO expert Xiao Wen that the survival of the prawn larvae requires a brackish condition. And later in 1972, mass culture techniques were first developed for commercial scale post-larvae production in Hawaii. And this prawn species actually possess a very high economic value, where a grade A prawn weighs between 2,500 and 300 grams of the prawn, price about 85 to 90 ringgit Malaysian. However, the problem of the aquaculture of this prawn species is that the production has been hindered by the whitetail disease. And the disease actually got its name from the clinical symptoms of the infected prawn, where you can observe a whitish muscle of the prawn when they were infected by the virus. And in Malaysia, the disease was first reported in 2012, where it resulted up to 100% mortality of the post-larvae prawn production in the affected hatchery. The disease is actually caused by the macrovacuum Rosenbergi nodavirus, which is a newly discovered nodavirus that infecting prawn species. So this macrovacuum Rosenbergi nodavirus is actually a single-stranded positive sense RNA virus, where its genome comprises of 2 segments of RNA, which is the RNA1 that encodes for the RNA-dependent RNA polymerase, and the RNA2 that encodes for the virus code protein. And this virus code protein gene is actually our target gene for the codon deoptimization. So we aim to design the live virus that has been attenuated through codon deoptimization in order to reduce the virus fitness in the host. And this is what we do. So for the codon deoptimization, the preferred codon in the gene was substituted for its respective unfavorable synonymous codon. For example, here, as you can see, the codon that encodes for the amino acid valine, the preferred codon will be the GTT and GTC, where it has a very high frequency compared to GTA and GTG. So for this preferred codon, it was substituted with the frequency of this codon were reduced as, for example, here from 12 to 5 and 6 to 1, and it was substituted with the GTG and GTA codon, where the frequency has been increased in the mutant design. So these substitutions were governed by the calculated codon weight and also the relative codon deoptimization index. So as for our mutant design, we have successfully reduced the codon adaptation index from 0.8 observed in the wild type to 0.6 that is in our mutant design. And also we increased the relative codon deoptimization index of the wild type capsid protein gene from 1.3 to 1.9 in the mutant design. So the advantages of our design is that the 125 synonymous codon substitution were distributed over the entire coding gene of this capsid protein, so which maximize the genetic stability. And it will be required an extensive mutation for the mutant virus to revert the substituted codon in order for it to regain the virulent phenotypes. So basically, we can claim that the mutant design here is genetically stable. So due to the synonymous substitution, so we didn't change any of the amino acid sequence. So thus our mutant virus is expected to possess an intact antigenic repertoire that is identical to the wild type, so that it can trigger the host immune responses similarly to the wild type virus. So after we have designed the virus gene, we synthesize and clone it in the cloning vector, and then we perform the in vitro transcription in order for us to obtain the viral RNA. So for here, we have 3 different viral RNA, which is the wild type capsid protein, the wild type RDLP, and also the mutant capsid RNA. And then we transfected this RNA into a susceptible cell line, which is the SF9 cell, in the combination of the wild type RDLP and wild type capsid protein for the wild type virus. And for the attenuated virus, we transfected the cell with the wild type RDLP and also the mutant capsid protein. So the wild type RDLP is meant to maintain the replicative properties of the virus in the cell. So what we can observe from the transfected cell is that the cells that transfected with the wild type virus shows cytoplasmic swelling and also very low cell count number, as you can observe from the figures here. And compared to the mutant virus, we observe very insignificant changes and slightly increase in the cells due to cytoplasmic swelling at 48 hours post-transfection. And up to 96-hour post-transfection, we can observe a very significant cellular aggregation in the cells transfected with the wild-type virus, showing the pathogenicity of the wild-type gene, compared to our mutant design, where we only observe a slightly increase in the cell size and also reduce in cell number. And this is the increase in cell size is due to the cytoplasmic swelling, and compared to the control cell, which is the non-transfected cell. So the findings is actually based on the known condition that the codon usage affects the mRNA translation efficiency. When the genes were encoded by the preferred codon, the abundance of connect tRNA will actually allows the faster translation rate compared to the genes that are encoded by the unfavorable or rare codon, where it has a very lack of connect tRNA. So it will have a reduced or slower rate of translation of the gene. Then this could result in the premature termination of the protein translation due to ribosomal stalling. And also the de-optimized codon actually will lead to a Wuber-based pairing during the translation. That is, this codon will be decoded by a synonymous tRNA species, which also will lead to a compromise of the protein translation efficiency. So we concluded from our preliminary study that we have successfully demonstrated a reduce in the virulence of the mRNA in SF9 cells, where the SF9 cell transfected with the de-optimized mRNA exhibited a very minimum cytopathic effect compared to the wild-type wild-type virus. That the results actually inferred that the virus pathogenicity was compromised due to the inefficiency translation of the codon de-optimized capsid protein gene. So we are currently in the process of rescuing the virus, wild-type and also the mutant virus from the transfected cell. And we're going to proceed with the in vivo study using the Altimia as our model organisms. So I would like to take this opportunity to thank the PhD student, Siti Nur Fatimah, who has been working hard on this study. So thank you for your attention as well. That's all from me.
Okay, thank you, Dr. Loh, for that wonderful talk. Okay, And now we will move on to the next one. Again, oh, I forgot. Let's give virtual claps to Dr. Low. Come on, virtual claps. This is a very responsive hall one, huh? Every time we hit new what do you call that? The high score of claps, huh?
Thanks.
All right,
Thank
so thank you
you.
again, Dr. Low. Again, please stay back later for the Q&A session at about 12:10. All right. And again, everyone with questions. Oh yeah, I do see questions coming in. Okay, so I will copy and paste the questions for the Q&A session later. All right, thank you, Dr. Low, very much. And
All
we'll
right,
move
thank you.
on to the next speaker, who will be presenting on transcriptomic analysis of chlorella sorokiniana for pigment production under moderate light intensity. And this will be presented by Dr. Noami Azman from University Putra, Malaysia. Dr. Siti Noami? All right, okay, we can see your slides and I can see your video. Can you try saying something, Dr. Siti?
Okay, thank you, Dr. Crystal.
Okay, great. The floor is yours.
Can you hear me?
Yes, everything is fine.
Okay. Okay, Bismillahirrahmanirrahim. Assalamualaikum and very good day to all the participants. So now it's my turn to present my study entitled Transcriptomic Analysis of Chlorella sorokiniana for Pigment Production under Moderate Light Intensity. So my presentation divided into 3 parts. Okay, for the introduction, what is chlorella species? Okay, chlorella species is one of the most popular macroalgae applied in many industries, for example, health and pharmaceutical. They are able to produce metabolites that possess various health-promoting activities such as antioxidant, antimicrobial, antibacterial, antifungal, anti-cancer, and antiviral that suit to that industry. The potential of producing different pigments by chlorella species also pave a new way for commercial application. They serve well in commercial application due to their adaptability to a various culture condition. So if they get an optimum light, carbon source, nutrient, and the biomass can produce a lot of various valuable metabolites such as protein, lipids, pigment, carbohydrate, carotenoids, and phenols. So in terms of pigment production, manipulation of growth conditions such as carbon dioxide, light intensity, and nutrient limitation were commonly used. For example, for light intensity, it has been proved to give effect on microalgae growth and the biochemical composition of the cells through the process of photoacclimation and photoadaptation. In terms of photoadaptation, the microalgae can change their composition, for example, fatty acid composition, pigment composition, their growth rate, as well as the respiration rate. If we introduce higher light intensity to the microalgae, they will produce higher amount of primary pigment, for example, chlorophyll A, B, and C. And if we introduce a higher light intensity, it will reduce the production of primary pigment and increase the production of secondary pigments such as zeaxanthin, beta-carotene, lutein, and astaxanthin. Meanwhile, if we introduce the higher than saturated level of light intensity, it may disrupt the chloroplast lamella and induce photoinhibition. So the specific analysis on the effect of genes related with the physiological changes was still unpromising. Most of the study are species specific. So it contributes the high variability in the transcriptional regulation of those different strains due to the distinctive epigenetic machinery, because when we maintain the microalgae in different conditions, it may contribute to the changes of the epigenetic machinery. So in the construction of microalgae system for commercial application, transcriptomic study could be more efficient and relatively economical compared to genomic study. It provides an initial and broad view of specific gene related to the treatment and condition use. So in our previous study, we have proved that moderate light intensity had changed the biochemical content and the morphology of the microalgae chlorella sorokiniana. Thus, further understanding on how it happens at the transcriptional level are very beneficial. So our objective of the study is to discover genes that encodes enzyme involved in the biosynthesis of pigment and carotenoids in the cholera sorokiniana through transcriptomic analysis. For the methodology, we allow the microalgae to grow until mid-log phase. Then we introduce moderate light intensity. In a normal condition, we use 10 micromole photon. And for the moderate light intensity, we increase to 100 micromole photon. And we allow the microalgae to grow for about 2 weeks until stationary phase. And we harvest the cell. Then the cell was subject to RNA isolation and do RNA sequencing using HiSeq 2000. And we do analyze on QC, trimming, de novo assemble. And from the transcript, we use to annotate for the functional pathway and also transcript expression followed by data interpretation and correlation. Okay, from the result here, we can see slightly changes of the color of the microalgae growth from very green into slightly green, yellowish green. And also we observe the changes of the morphology. The size of the microalgae is bigger compared to normal. Okay, from the sequencing analysis, we could get 60 million raw data, and after trim and quality filtering, we get about 93.63% high quality pair and reads. Okay, so we do de novo assemble, then we can get transcript about 18,310 with the longest transcript about 16,000 base pair. Okay. Then we do functional annotation, and we successfully found enzyme that encodes for essential metabolic pathway. And 99% we found the enzyme. Then this is the result for differential gene expression, where we find some of the main metabolic pathway were upregulated and downregulated. For the metabolic pathway that upregulated were lipid metabolism in the production of unsaturated fatty acid, as well as metabolism of cofactor and vitamin, and biosynthesis of secondary metabolites. For the downregulated pathway, we found glycolysis, starch metabolism, and TAG biosynthesis were downregulated. Okay, what I want to focus here is the production of carotenoid biosynthesis. From the figure here, as you can see, the production of beta-carotene is downregulated and the production of lutein is upregulated. Okay, we found the genes that responsible for the upregulation of lutein are carotenoids, lycopene epsilon cyclase, and epsilon ring hydroxylase. Meanwhile, for the downregulation gene responsible for the beta-carotene, phytoin dehydrogenase and carotenoid cleavage deoxygenase. So, overview of the carotenoid biosynthesis here, we can see from this figure, the route for the production of lutein from lycopene was upregulated. Meanwhile, for the production of zeaxanthin, astaxanthin, and beta-carotene were downregulated. Okay. So we have validated our result with the RT-qPCR. And we found that there are two routes leading to lutein production from alpha-carotene, which is beta ring hydroxylation to xenoxanthin, and also epsilon ring hydroxylation to alpha-cryptoxanthin. So our transcriptome data, which is the second step after beta ring hydroxylation, which is epsilon ring hydroxylase, was upgraded, leading to lutein production, was similar found in Zhao et al. So in this treatment, lutein production was more favorable compared to the other carotenoid production. This transcriptomic analysis provide a broad overview of an important metabolic process, which can efficiently build a hypothesis that can guide future detailed studies on improving the carotenoid production in this and the other microalgae. As a conclusion, Genes that encodes enzyme involved in the biosynthesis pigment and carotenoids in Chlorella soriciniana through transcriptomic analysis were identified under moderate light intensity. So that's all from me. Thank you for your attention.
All right, thank you, Dr. Siti Noani. And again, please stay back later for the Q&A session at 12:10. Everyone, please give virtual claps to Dr. Noani for her wonderful talk. And I see a lot of virtual claps coming in. That's good. Okay.
Thank you.
So we hope also that I have questions for you later. Okay, Dr. Noani. Okay, thank you very much for the talk. Now we'll move on to the next speaker. The next speaker will be Dr. Fazana Yasmin, who is from Lincoln University College, to present her talk entitled Growth Promotion of Sweet Potato, or Very Sweet, by IAA Producing Rhizobacteria. Dr. Fazana?
Hi. Thanks, Christian. Okay, Assalamualaikum.
Dr. Fazana, sorry, can you please share your slides?
Oh, okay.
And if you don't mind, can you turn on your video as well?
Okay. Can see my slide?
Yes, can see your slides. Can you turn on your video?
Okay. Start my video.
Hello, Dr. Fazana.
Hi.
Okay. You're good to go.
Okay.
The floor is yours.
Okay. Assalamualaikum. I'm Dr. Fazana from Department of Biotech, Lincoln University College. Thanks to everyone and thanks to ICMBB for giving me this opportunity to present my research project. So first of all, I introducing with my topic. My topic, growth promotion of sweet potato IA producing rhizobacteria. So here, first of all, I introduce the introduction. Sweet potato is one of the major staple foods in several countries, including Asia and the Pacific Island. So in Malaysia, sweet potato is the second most important root crops after cassava. It is also good source of carbohydrate, beta-carotene, thiamine, riboflavin, folic acid, ascorbic acid, and minerals. It also serves as noodles, products, bakery products, cereals, dessert preparation, and snack foods. So sweet potato, the sweet potato cultivation in Malaysia is currently declined due to the infection of disease, non-availability of agricultural land, nutrient deficiency in soil, and labor cost, marketing issue, and high input of chemical fertilizers. Several alternative methods are available for enhancing the crop performance. One of the methods to sustain production is through the application of beneficial microorganisms, such as plant growth promoting rhizobacteria. These plant growth promoting rhizobacteria can produce the phytohormones. These phytohormones improve plant growth by increased uptake of nutrients. So indolic acid one is the phytohormone that is regarded the hormone synthesized by the PGPR. So this indolic acid produced by bacteria is involved in several mechanisms of microorganisms and plant interaction. Indolic acid may be induced to either grow faster or better due to the stimulation of cell division and cell differentiations. So, and also positively influence the development of root system. So this could increase crop productivity and lower nitrogen fertilizer. So objective of this study to determine the effect of IA producing rhizobacteria isolates on the growth of the sweet potato. So let's go to the materials methods. Materials method, a pot experiment was conducted in the glass house at University Putra, Malaysia. So bind cutting of sweet potato was grown in the 2 kg of sterilized sandy soil. And there are 4 treatments. One is the control, second one SP1, third one SP2, and the fourth one is the Azospirillum bacillus SP7. SP1 and SP2 bacteria isolated from the sweet potato rhizosphere in Malaysia, and Azospirillum bacilli isolated from the Brazil. So an inoculum concentration of 10 to the power 9 colony forming unit per ml was applied into the respective pots. Each pot was inoculated at planting and 2 weeks after planting with 5 ml of inoculum per pot per applications. The experiment was run in a completely randomized block design with 3 replications. Plants were harvested at 30 days after planting. The fresh weight of plant tops and roots are determined, and that the dried plant samples example that leaves and stems. Stem samples are ground and digested with sulfuric acid and hydrogen peroxide using the block digestion following the microgelden method. So nitrogen, phosphorus, and potassium are determined using the autoanalyze, whereas calcium and magnesium are analyzed by atomic absorption spectrophotometer. And the total population of bacteria in soil was determined at harvest by using total plate count techniques. So indolic acid, the concentration of indolic acid determined in the method Saror et al. 1992. So all data were analyzed the statistical analysis systems. And difference among the treatment means determined using the Turkish standardized dense test comparison method P equal to 0.05. Result and discussion. First, we into the result and discussion. This table highlighted the effect of rhizobacterial inoculation on growth parameters of sweet potato plants. This experiment clearly showed the beneficial effect of the rhizobacteria isolate to stimulate initial growth of the sweet potato plants. Inoculation with SP1 and SP2 improve root and top growth of the sweet potato plants. This increase could be ability to SP1 and SP2 produce high level of indole acetic acid and that stimulate the plant shoot and root growth. So the IIA indole acetic acid would stimulate root growth and development by promotion, root initiation, cell division, and cell enlargement. So growth promoting effects of PGPR inoculation are mainly derived from the morphological and physiological changes in inoculated plant roots and enhancement in water and plant nutrient uptake. So nutrient uptake in shoots. Improved plant growth with inoculation was due to increase the uptake of nitrogen, phosphorus, and potassium of the plants. So plants inoculated with SP1 and SP2 showed significantly higher uptake of NPK, calcium, magnesium compared to the control. This is the table highlighted that one. So the increased uptake of essential nutrients may be attributed to the stimulation of plant growth and development, which resulted in increased diameter and mineral accumulation in stems and leaves. So bacterial inoculation has a beneficial effect of sweet potato has been observed by Farjana et al. And Durham et al. They suggested that inoculated sweet potato plants grew faster and absorbed more nutrients than uninoculated sweet potato plants. Population of bacteria and IOA concentration in soil. There are significant differences in soil bacteria population and IOA concentration between the different inoculation treatment. The highest population of IOA and bacteria population were found in soil inoculated with SP1. So it has been reported that 85% of rhizobacteria are able to synthesize indole acetic acid, which colonize the seed and root to able to induce the cell proliferation and enhance the soil enhancement in IA in the soil. So let's go to the conclusion. What is the conclusion? It might be concluded that inoculation with IA producing rhizobacteria significantly improved the early growth of sweet potato plants. Plants inoculation with SP1 and SP2 bacteria increase growth, tops and roots and nutrient uptake and PK of the sweet potato plants. This study indicates the bacteria strain have the potential plant growth promoters and may be used as a bioenhancer. That's all. Thank you.
All right. Thank you, Dr. Fazana,
Yes.
for the wonderful talk. And again, please stay back for the Q&A panel session later. All right.
Okay.
And let's everyone give virtual claps to Dr. Fazana for her wonderful talk. All right. So now let's welcome the next speaker. And the next speaker is Miss Eileen C. Tiao Ning, who is from University of Malaya. And Miss Eileen would be presenting her project entitled Potential Muscle Activity Disturbance in Penaeus monodon during acute hepatopancreatic necrosis disease infection, inference through gene expression, calcium concentration, and microRNA. Miss Eileen, the floor is yours.
Okay, thank you, Dr. Pisto. So good afternoon, everyone. I'm delighted to have opportunity to share our study today entitled Potential Muscle Activity Disturbance in Penis Morodon during acute hepatopancreatic necrosis disease infections, inference through gene expression, calcium concentration, and microRNA. So now let me start with some general information on aquaculture. Aquaculture plays a crucial role in the food system. It is provide the protein and various macronutrients that are needed for human. While shrimp is one of important aquaculture because it contains high level of protein, minerals, and also low in saturated fat content. So that the global demand for the shrimp is significantly increasing nowadays. However, according to the Global Aquaculture Alliance survey in 2019, they mentions that diseases is the major issues and challenges in shrimp aquaculture because diseases will cause massive shrimp mortality that will affect the productions, and hence the economy loss can be bigger. While HPND is one of the important diseases that is most people concerned today. HPND was originally called as early mortality syndrome, and it is a new strain of Vibrio parahemolyticus bacteria. It will cause the 40 to 100% of mortality within the 35 days in the shrimp pond stocking. Besides that, the major symptoms of this disease include reduced growth, lethargy, prior to white atrophied hepatopancreas, and empty stomach. So from this figure, we can show the differences between the infected shrimp and also the uninfected shrimp. So the infected shrimp shows a wide coloration of hepatopancreas compared to the uninfected. So moreover, this bacteria will colonize in the stomach and further produce the toxin to damage the hepatopancreas. So there is another question arises, which is, will these bacteria damage the muscle tissue as well? Because muscle tissue is a major organ that will be consumed by human. So that the objective of this study is to determine the penis morodon muscle integrity during HPND infections for investigating the gene expression, microRNA expression, and also the calcium concentrations. The gene selected in this study is dystrophin gene, which is used to regulate the muscle functioning and muscular integrity preservations. While for the microRNA expressions, first is microRNA 4286, which is targeting the sarcoplasmic calcium binding protein used in muscle contraction and relaxations. While for another microRNA is microRNA 107B, which is used to targeting the P53 inducible protein for the cell apoptosis and DNA repair purpose. This figure shows the overall mechanism that we speculated in this study. First is HPND infect the penis model, and the nucleus will express the dystrophin gene to maintain the muscle integrity. In the meantime, the nucleus also will express the microRNA, which is microRNA 107V, to induce the apoptosis, while for the microRNA 4286 will inhibit the cyclophosphamide calcium binding protein to avoid the translocation of calcium ion and store in the cycloplasmic reticulum, so that a lot of calcium ion will be accumulated in the muscle cells. For the methodology part, first, the bacteria will be isolated from the infected strain and enriched in the trapezoid medium, supplemented with the sodium chloride. And this bacteria will further challenge into the penis model strain using the immersion method, and followed by the collection of strain in different time points. After that, the strain will further proceed with the RNA extractions and cDNA conversions for the dystrophin gene expression and microRNA expression analysis. Besides that, the muscle cells also further proceed with the calcium concentration determinations using the calcium assay kit based on the calorimetric method. In the result, first is dystrophin gene expression quantification analysis. From this figure, we can show that the dystrophin gene was upregulations at 3 post-infection hour, and peak was detected at the 6 post-infection hour. These upregulations was significantly reduced at the 12 post-infection hours, but slow increase from 12 to 36 post-infection hour. So the suffering actually having a domain that is associated with the binding of intracellular calcium ion, so that we further tested on the calcium concentration determinations. So from this figure, we can show that there is slight downregulation and reduction in the calcium concentrations from 0 to 12 post-infection hour, and the lowest peak at the 6 post-infection hour. This was followed by the sharp increase from 24 to 36 post-infection hour, and the peak, highest peak at the 36 post-infection hour. So this sample will further validated using the microRNA expression analysis. And this graph, you can see that the microRNA 4286 was upregulation in the infected strain sample compared to the uninfected strain sample. So it means that its target cyclophosphamide calcium binding protein is downregulated in the infected strain. So it means that a lot of calcium ion will be accumulated in the muscle cell, unable to storage into the cycloplasmic reticulum. While for the microRNA 107V, is downregulated in the infected strain compared to uninfected strain. So it means that its target, which is the p53 gene, is upregulated. So it means the muscle cell is induced the apoptosis and also the DNA repair to avoid the proliferation of the damaged muscle cells. So in summary, based on the result, we can see that the dystrophin genes were expressed highest at the 6 post-infection hour, while the calcium concentration was reduced in the muscle cells from 0 to 12 post-infection hours, and the lowest was detected at the 6 post-infection hour, while the highest calcium concentration was detected at the 36 post-infection hour. For the microRNA expression analysis, we noticed that the microRNA expression also was changed in the HPND infections. One is microRNA 4286 was upregulated, means that its target cycloplasmic calcium binding protein was downregulated, while for the microRNA 107V was downregulated, means that its target p53 mediated apoptosis gene was upregulations. In conclusions, the toxic HPND metabolites could lead to muscle protein degradations. So it means that it will lead to the strain muscle loss. So this is my reference. Thank you for listening.
All right, thank you, Ms. Eileen, for the very interesting talk. And can I have everyone to again give virtual claps using the emoji reactions? Yeah, we also have a lot of claps for you, Ms. Eileen. So again, please be reminded to stay right after this for the Q&A panel session. And now we will then move on to the next speaker, who is Miss Maya Erna Nathan, and she has the honor of being the last speaker for this morning session. Miss Maya, can you please share your slide?
Yeah.
Miss Maya is from University Kebangsaan Malaysia, and she will be presenting her research entitled GCMS-based metabolomics and the effect of fatty acids dietary supplementation on the survival and innate immunity response of hybrid groupers against vibriosis. Wow.
So can you see the slide?
Miss Maya, sorry, can I have your video on, please?
Oh, yeah.
All right. Okay, I can see you. And the floor is yours.
Thank you. Assalamualaikum and a very good afternoon, everyone. Thank you for joining me in this oral presentation for the 4th International Conference on Molecular Biology and Biotechnology. My name is Maya Erna Nathan, and I am from University Kebangsaan Malaysia. And today I would like to present to you my research study entitled GCMS, is metabolomic and effect of fatty acid dietary supplementations on the survival of innate immunity response of hybrid grouper against the vibriosis infections. Okay, this presentation will be covered into 5 main sections, which is starting the introduction, followed by methodology, based on discussions, conclusion, and finally the teaching effect. Okay, let me start by giving you some background information about the study. Grouper represent about 30% of global marine fish production, and in Asia itself, the largest grouper producer China, followed by Indonesia and Taiwan. As in Malaysia, apart from the local demand, Malaysia also export the grouper production in Singapore. Because of the high market demand and also price, the grouper production in Southeast Asia can reach to 300,000 tons per year. And for the price, the grouper may reach to $100 in Hong Kong and also China. As for in Malaysia, the grouper price may reach to 80 to 100 ringgit per kilogram in Malaysia. So as the productions of aquatic element increase, they also easily exposed to some diseases such as bacteria, viruses, and also parasites. For example, vibriosis disease is caused by the Vibrio bacteria, and for viral nervous necrosis is caused by the virus known as beta norovirus, and also aeruginosis infection caused by the parasite known as the Aerugulus colitis. So, in aquaculture industry, the vibriosis has been one of the main problems that caused the mortality, massive mortality animal culture. So what is with the family vibriosis? Yeah, with about 1 bacteria with the root shape, this vibriosis can cause 50 to 100% mortality, and the symptoms that can be found such as skin rot, swollen lesion on the skin, gill necrosis, ulcer, bulging eyes, and lastly can cause death in the fish. So this disease might occur because of the poor management practices or the intensive farming technique that being applied by the farmers. So as today, majority of farmers are using conventional method. So how to overcome this problem? Because this problem may decrease the aquatic animal production and also cause extinction. So majority of the farmer using conventional methods such as antibiotic. But however, in the long term, by using the antibiotic, it can develop the pathogen-resistant bacteria strain, and also can the antibiotic will no longer effective toward the pathogen outbreak. And also by continuing using the antibiotic, it can also cause accumulation in the residue, antibiotic residue, and which cause or will be harmful to the human consumption and also environment. So to overcome this disease problem, a new approach dealing with this problem is suggested. For today, I will showing you the effectiveness of these using immunostimulants in increasing the immune response of the grouper fish. For your information, immunostimulants are known as the compounds or chemicals that can stimulate the immune system activity, such as phagocytic cell and lysozyme activity. So in this study, we are developing an eco-feed adaptive as the immune stimulator for the grouper fingerlings. We chose this stimulation for the fish feed because it's easier to handle and it's not stressful for the fish. Other than that, feeding approach is also very suitable for the fry fish and also other smaller fish. So methodology for this study, we have two methods that involved. First is GCMS analysis, and second is the evaluation of new feed formulation. In GCMS analysis, grouper were challenged with the vibrio varmiticus for over 21 days. We challenge with vibrio varmiticus, and then we observe it for 21 days. And then we sample the survivor grouper and we extract the metabolites and we send the sample to GCMS, or known as gas chromatography mass spectrometry analysis. So the list of metabolic compound will then analyzed using the net CDF, copy, and also an IC library. So here are the metabolite profile that from the survivor group of fingerlings that we identified, and from this result, several metabolites from the fatty acid group are shown a significant role in immune response after vibrio infection. So for this study, we choose 4 fatty acids, which is the palmitic acid, stearic acid, behenic acid, and also uric acid for fish feed formulation. We choose this 4 fatty acid because it's not only they're highly abundant in the survivor fish infected with vibrio, but they also, as the additional ingredient in fish feed, this fatty acid compound is very easier to be found and produced, and also it is inexpensive compared with other fatty acids listed here. So this is showing the process of fish making, where ingredients were mixed together and then were extruded through the mixer, and the feed were oven dried before the pellet was obtained and ready for feeding experiment. So for feeding experiment, the grouper will be feeding with a new formulated fatty acid for 6 weeks and challenge with and observation will be conducted for 1 week. So after 1 week, it determines the survival and also the immunity assay or immune response of the fish. So from this graph, we can see that survival rate of grouper that feed with folic acid have show the highest survival rate compared with control and also other fatty acid group. And then for the immunology assay, where 3 immunology assays were conducted, which is lysozyme assay, respiratory assay, respiratory versus activity assay, and phagocytic assay. We also see that grouper that feed with folic acid give the highest immunology response after infected with the vibrio compared with control and other fatty acid formulated feed. So based on the result, we can conclude that the grouper fingerling feed with folic acid formulation give highly significant survival rate after infected with vibrio varmiticus. And also this folic acid feed formulation can successfully eliminate the grouper fingerling response, which can lead to the higher resistance against the vibrio infection in the future. So lastly, for the future effect, we hope that this finding will give impact not only to the farmers but also the economy and also the environment. year. For impact to the farmer, we hope that mortality rate caused by the vigorousness in group culture could be reduced, and we hope we can produce a potential health promoting fish feed supplement for commercializing in the future. And for impact to the economy, we hope that this crisis in aquaculture industry could be reduced, and we can produce high fish production to fulfill the market demand. And lastly, to impact to the environment, we hope that we can reduce the pollution that caused by the excessive use of the antibiotic or other chemicals that we use in the aquaculture industry. I think with that, I end my presentation today. Thank you.
Okay, thank you, Ms. Maya. Let's have people giving the virtual claps again. Virtual claps, come on, virtual claps for the last speaker for the morning session for today.
Thank you.
All right, thank you. So now we will have the Q&A panel session. So may I invite all the speakers, starting from Prof. Jennifer, Dr. David, Dr. Low, Dr. Siti Noani, Dr. Fazana, Miss Eileen, and Miss Maya. May I invite all of you into the Q&A panel session. If you guys don't mind, perhaps you can turn on your camera as well so that everyone can see you guys again. Yeah, I see Eileen, I see Prof. Jenny, I see Dr. Noani, I see Dr. Fazana. How about Dr. David? Because actually we have a question for Dr. David. And yes, David, there you are. And Ms. Maya, I think everyone is here. Okay, so let's begin the Q&A session. And let me read off the first question first. I'm just reading it all by, the order that they came in, yeah? Okay. So David, you have a question. Oh. So this is from T Hui Zi. T Hui Zi, are you in the house? T Hui Zi? If you are, please indicate that you are around because you are going to have your question being answered. T Hui Zi? Not sure where he or she is. Okay, that might, it's okay. I'll just read out the question and David can try to answer the best you can. So Ti Hui Zi, I'm not sure what the affiliation is because he or she has not replied me on that. Says that thanks Dr. David for the wonderful talk. Given that the growth condition is one of the limiting factors and you have the genomic data for the palm from different locations, do you consider looking into the soil microbiome as well to link the location or growth conditions with their genetic differences to identify more species traits that can potentially help to improve Well, we have a partial answer from someone.
Yes, we do. We have a small team of scientists looking at the soil microbiome. It's relatively small scale. It's quite challenging in terms of just the significant breadth of sampling that's required to really understand microbiome on a commercial scale. But what we did is for in particular, the inland field that we planted back in 2016, we've been sampling a number of different sampling points on a routine basis about every 3 months and looking at the microbiome and the changes across the field and the changes with season and starting to identify different microbes. And we're putting that alongside nursery experiments where we're looking at presence and absence of different microbes and impact of fertilizer on them and putting that together in a bit of a long-term study. But certainly our focus at the moment is really looking at the interaction of different genotypes and their response to different weather patterns first. Yeah.
I see. So weather patterns come first, and after that, then we only look at the phenotypic conditions to see what it links to. Okay. Ti Hui Zi, I hope that answers your question. If you are there somewhere out there, okay, but you can always watch back the recording to get Dr. David's answer. All right. Do feel free to contact Dr. David if you require further clarification on his answer. All right. Okay. Thank you, David. And I have the next question, although I think Dr. Low, you have already answered the questions in the chat, yeah, Dr. Low. But maybe I'll just read it out anyway, in case anyone has missed looking at the chat. So we have a question to Dr. Low Chen Fei from Christine Yan from Monash University, who asked, I'm curious to know how to apply these findings in controlling the disease in aquaculture farms and how you translate it into real world application. She also asked further how to determine cordons and which cordons to increase or decrease and what are the determining factors. So maybe Dr. Low, if you can perhaps summarize the answer to the
Okay.
many questions.
Yeah. So our aim is to develop an attenuated, as I answered in the chat box. So our aim is to develop attenuated virus as a live vaccine to control the disease. So next we're going to rescue the virus from the transfected cell and then try to infect the virus into the Artemia, as Artemia is known to be one of the potential carrier of the virus. And also the Artemia is fed to the prawn larvae as a live feed. So we're thinking to use this organism as our vector to deliver this live vaccine. But of course, we have to perform more study to really understand and evaluate the safety of using this attenuated virus. And then for the next question on the codon de-optimization, so we actually did it randomly. So the de-optimization is actually by random, but then it is actually governed by the CAI value and also the RCDI value. So we control the de-optimization so that it didn't go too far away that the gene cannot be translated. So and then we didn't target any specific region because the substitution is actually synonymous. So we didn't change any protein sequence. So the virus still remain the wild type structure in terms of the protein structure and also the protein sequence. So I think I answered all the questions, right? Did I miss anything?
All right, thank you, Dr. Low, for summarizing everything. And oh yes, okay, I see questions coming in now. And I hope that Christine is happy with your answer, Dr. Low. And I think you already have an invitation for collaboration from her. All right. Okay. And oh, I have a question from Aizat from UKM for Prof. Jennifer, who says that thanks, Prof. Jenny, for the insightful talk. How stable is the RNA silencing in the orchid? Would we see any phenotypic differences in later generations? Prof. Jenny?
Okay, thank you. That's a great question. And it depends on the method. So using our method where we just treat with double-stranded RNA is just going to get into the cytoplasm and it will never alter any nuclear content. So there is actually no epigenetic changes possible either in this instance. And I think that is also quite comforting to those who are worried about the RNA vaccines, that when we use these kinds of RNA treatments, it's a transient effect. But if you wanted to, having tested genes and found that you like the change, you could then introduce those into the nucleus and make the cells make their own double-stranded RNA to get a stronger effect. And so this is one of the things that the technology is useful for. You could convert that to an inherited change through other mechanisms. So if you want to silence the gene, of course, you don't have to use double-stranded RNA. You could use CRISPR knockouts or other methods as well. So not using double-stranded RNA, not inherited, but you can then go on to use other technology if you want the trait to be inherited.
Isaac, I hope that answers your question. Now we can open for oral mode of Q&A if you guys would like to be a bit more interactive with the speakers. It's not every day that we get to speak to Professor Jennifer, you know. Although I have that privilege too. Oh.
Anytime for you, Crystal.
Okay, perhaps let me ask, you're all very shy here. Either that or they have all, you know, go and get their lunch already or something. So, okay, let me ask a curious question myself, Prof. Jennifer, because I have a friend who is a orchid nut. Okay, so she is basically spending her life, like, you know, breeding orchids and growing orchids and stuff like that. So do you foresee that this the dsDNA silencing method might be something that is possibly useful for the future hobbyists in orchid growing and orchid agriculture?
Yeah, I definitely see the potential for pest control, disease control. And I think if you look at what's happening in the commercial space, that's where all the excitement is at the moment. I think making phenotypic changes is more for sort of doing lab level experiments than for any commercial use. Maybe for hobbyists, it would be fun too. But definitely for crop protection, there's very good indication that this is going to be a commercial product, maybe not for orchids first, but for many field crops, this sort of technology. So I think it's just a case of people whittling down the prices and sorting out the legislation for applications of the technology. But a lot of the big agri-tech companies are having patents in this space and are looking quite aggressive. So I think we will see it, not just for crops though, it's fairly easy to do for any kind of virus. So once you know what your virus is, and as I mentioned, other pests and diseases, insect pests are a possible target as well. So it's quite exciting, yeah.
Okay, great, thank you. I'll let my friend know, it's not something that's gonna be available in the next year or so. All right, thanks for Jennifer. And we have a question from, who is this? Suhaila Sulaiman. Okay, I'm not very sure where you are, Suhaila Sulaiman. And she has a question to Dr. Siti Noani. So Dr. Siti, the question for you is, like playing a game show. Apart from transcriptomic analysis, have you done any other omics in your research? If so, do you mind to briefly share about it? Quite a general question, huh? Okay, Siti Noani.
For now, it's just transcriptome analysis. I've done on mRNA, microRNA transcriptome analysis also. So I found some interesting microRNA that have controlled the production of this pigment production in microalgae cholera.
Okay.
Other than transcriptome analysis, I'm not done yet.
Okay, so maybe Suhaila is inviting you to do some other kind of analysis, huh? Okay, Suhaila, I hope that answers your question. We have a question for Dr. David from a Nazrin. Okay, so David, all your question askers are all pretty anonymous. I'm not very sure where they're from. I don't even know their full names. So Nazrin is asking, how do you define the best seeds to be selected? Is it seeds that contain the highest number of SNPs that you are interested in?
Okay, good question. Basically, yes. So we have 1,000 markers that we have associated with different yield traits. So we know which alleles of those have the highest impact on yield. So we would be able to rank any particular seed that we sample, but we're also able to rank the parental palms, basically the mother palms and the pollen, to see their ability to be able to combine to give progeny that have the highest combination of the right SNPs for yield. And of course, the other thing to do is to genotype the seeds that are produced and make sure that they're pure and true to type and they're not from some stray pollen or some mix in seed production. So we apply both of those processes. Yep.
Okay, Nazrin, I hope that answers your question. I guess so. All right, thank you, David. Yes, he said yes, thank you. All right. Okay, can I have more questions? There's so many people here and we have a pretty large panel for this morning and we have about 3 minutes left for Q&A session. Once in a lifetime chance to ask questions to this panel. Don't be shy. Let me just check the chat again in case I miss anything. Anyone who would prefer to ask oral questions, you may also do so if you feel that typing takes too long. Okay, maybe while waiting, maybe I'll ask a question to Eileen. So Eileen, from your research, are you a PhD student, by the way, Eileen?
Yes.
You are, okay. So, and you're under Professor Subabasu, right?
Yeah.
Okay. So where do you think your next step of your research would be? So if you were to continue in this project and work further, perhaps as a postdoc fellow or something, what else will you be doing with the project?
Actually, I'm doing the string virus project for the treatment as well. Yeah. For HPND, I think we'll also towards to the treatment application as well. Yeah.
Okay,
For
so
the
you
future, yeah.
Okay, so you wish to go into the treatment part lah.
Yeah.
Okay. What about Dr. Fazana? What do you foresee will be the next step in your project? You're muted, Dr. Fazana. Okay. All right.
So this time I see the glasshouse, the plant is growing good or no. If plant is growing good, that I need to transfer to field experiment. I use that IA producing vector applied to the field experiment. This is my next target. Then we can get more sweet potato. In the pot, we cannot get more sweet potato. In the field, I can get more sweet potato and bigger. That's why.
MPO is over, huh?
Yeah. Okay, that's all.
Okay, thank you, Dr. Fazana.
Okay.
And Miss Maya as well. Maybe what's the next step of your project?
The next step of the project, I think, because I'm doing the metabiology work, so maybe we will try to do the using the proteomic approach or transgenic approach and so on that, so we can understand more about the immune response of that the glucose. It will be interesting to find out what is happening in their immune response pathway.
I see. Okay. All right. Well, it is 12:45, and this is the last call for questions. I will close the call for questions in maybe 10 seconds if there's no indication from anyone for questions. 10, 9, 8. I always do this countdown in class. No, when they're all online students, you don't even know whether they're actually there or not sometimes. 7, 6.
Crystal, I have a question.
Wow, okay, Prof. Suba, you have a question. Oh my God, this is scary.
I have a question for I sorry I missed the whole morning session. I really wanted to, but I really missed it because I had to attend an evaluation. But looking at the whole session, looks like it had ended very beautifully. Everybody asked very nice questions. So the question here is to Chin Fei. Chin Fei, I was very intrigued with the time that I entered when you said that you're going to the codon deoptimization region, that you're going to put it in Artemia. Have you done that? Have you done that part? And have you looked at the expression level and its efficiency in the diet?
Not yet, Prof. Actually, we are now at the cell culture stage. I mean, in vitro stage. We are working on the cell. So we are now trying to rescue the virus from the cell, and then later on only we can actually perform the in vivo study using the Artemia.
So
we are not.
So the cell culture, what cell culture are you using?
We're using SF9 cell.
Oh, okay, thank you.
Yeah, it's an insect cell line. Yeah.
Thank you. Very interesting project. Thank you.
Thank you, Prof.
Right up the same alley as you, Prof. Suba.
Hi, Crystal.
Okay, thank you very much, Prof. Suba, for the question. And I see a Raja Indra who turned on the turned on the camera, sorry, and not sure where did he go. Raja Indra, are you around? Do you want to ask a question or something? Raja Indra Putra? No? Okay, I guess not. Oh, hi, Suba. Nice to see you again. Okay, so yeah, and thanks for the last question just now. It's a nice close to the Q&A session for today. And let me just continue the 5-second countdown in case anyone else wants to ask the question. Last minute question, 5, 4, 3, 2, 1. Happy New Year! Just kidding. All right, so that ends the Q&A session for today. Thank you very much to all the speakers for today, from the plenary speaker, Dr. Jennifer N. Hare-Krishna, to the invited speaker, Dr. David Ross Appleton, and all the oral speakers, and have a very nice afternoon. And do please continue to join us at 2 o'clock, where we will then go to the poster presentation session. So a gentle reminder, if any of you are judges or chairpersons for the poster sessions, please be reminded to go to Hall 1 for the poster sessions. Again, thank you to everyone, and virtual claps all around. Yay, virtual claps. Wow, virtual claps hitting the roof. All right, thank you guys so much. Have a nice day.
Okay, thank you.
Good afternoon, everyone. Welcome back to the afternoon session for the 3 minutes poster presentation live Q&A session. So as I have projected on the screen, kindly go to the breakout rooms that you're interested in. To all 3 minutes poster presenters, make sure you're in the right room. Judges, please make your way to the breakout rooms as well. Thank you. Good afternoon, everyone. For those of you who are still in this hall, kindly make your way to the respective breakout rooms. Please follow the instructions that is being broadcasted on your screen right now. Thank you.
Amira, this is Dr. Eugenie. Amira, I have updated the app. And when I click on your breakout rooms, it says breakout rooms in progress. I click on breakout room F. Then it says breakout room in progress and it's blank. There's nothing after that.
Okay, let me just check with the technical team. But you are able to see all the different breakout rooms.
Yes, just now I could see and I could click on F. And it says breakout room in progress and there's nothing.
Okay. For those of you who are still here, kindly make your way to the respective breakout rooms to watch the Q&A session running live at the moment. And please ensure that you have got the latest Zoom app installed in your devices. The instructions for this can be found in the welcome kit that has been sent to you a few days before. Thank you. Good afternoon, everyone. I see that a lot of you are still here in the main room. So the 3 minutes poster presentation Q&A session has already started in the breakout rooms. Kindly make your way to which breakout room that you want to enter. Follow the instructions that is being shown on the screen right now. Thank you very much.
having a pot store.
Hi everyone, can you hear me? I'm Dr. Chandra here.
Yes, anything, Dr. Chandra?
Am I in correct hall? Am I in hall B?
No, this is the main hall. To go to your respective breakout room, kindly follow the instructions that is on the screen right now.
On the screen. Okay, I can see. Okay.
Hi, this is the main hall. If you want to go to the breakout room, kindly follow the instruction that is on your screen right now. Click on the breakout room icon and choose the breakout room that you're supposed to go into. Thank you. For those of you who have just entered Hall 1, kindly follow the instructions that is on your screen right now. Please enter the respective breakout room following the instructions. Thank you. Hi, if you're here and you're not sure what you're supposed to do, kindly look at the screen and follow the instructions to join the breakout rooms. Thank you.